numerical data is usually organized as some arrays of numbers. It might be lists of numbers or some large rectangular arrays of numbers, or maybe even multidimensional arrays. Linear algebra gives tools to work with such arrays. Namely, we apply some arithmetic operations and algebraic operations and even some abstract algebra to work with such arrays, to produce one array from other ones, etc. What are connections of linear algebra with other branches of mathematics? For example, with calculus, if you took the calculus courses. In calculus, we study more or less complicated functions, maybe functions on a lot of variables. For example, x1, xn, and yx will be will measure the value of the function so that it can be a multidimensional graph of this function. For example, this, and the coordinate net on this graph looks like following. So this is a graph on some function y is equal to f of x, so that there might be some maxima of this function or minima, or maybe a lot of maxima and minima, and here might be some increasing toward this arrow and maybe decreasing here, so that there are some properties of function. But if the number of variables is very large, then the methods of calculus is very difficult to apply, because we should differentiate some strange formulas and to find some rules of complicated equations and so on. If the number of variables 10 or even 100 or even 1 million, so the methods of calculus are almost impossible for more or less complicated functions. But locally, each function look at this local part. Each function has a very simple structure. If it is standard analytical function, then locally it usually looks like a kind of plane or a line, so that if you have some x1, xn variables, then this locally around, say, this point, you will see such a plane, so that, or so something which we call hyperplane, some picture which is which satisfies the equation a1x1 plus anxn plus some constant c. So that this is the equation of a hyperplane, and this is a very easy form of function. Using such a hyperplane, you can find the minima and maxima of the function if the hyperplane is horizontal, and you can find the direction of the increasing of the function only using this hyperplane, and so on. So to investigate complicated functions, you need only to investigate some hyperplanes, and if you need or line in the one-dimensional case. So that but in this situation we can provide a lot of computations with very large set of variables, even billions of variables, and then you apply methods of so-called linear algebra. You take, for example, one array of a coefficients and then multiply it by an array of x coefficients, and then to parallelize it and to calculate the sum, this sum, so that you apply methods of linear algebra. Because these methods are very distributable, and you can parallelly calculate a lot of things like this, so that these methods are often useful in many applications, such as not only machine learning but any investigation of data, including, for example, statistics, engineering, and so on, even in every mobile phone, and in for example, in every computer and many other modern devices, you have some algorithms of linear algebra inside them. We'll study some ideas in which these algorithms are based. Usually data is organized as arrays. The one-dimensional arrays, that is lists or columns, are called vectors, and some rectangular arrays are called matrices. Now let us consider operations which could be applied to them. An n vector is just a tuple of n numbers. They can be organized as a list or so on, but any tuple of n numbers is called an n vector. Maybe you know that vectors are arrows, or the vectors are, for example, in some programming languages, a vector can be an array of numbers of any kind. But now in linear algebra, n vectors are arrays of n objects. Later we'll consider also abstract vectors, but let us concentrate now on these ones. For example, one vector is just one number, so that the set of all one vectors is the set of real numbers. The n space is the set of all n vectors, so that set of all n tuples of numbers. So it is denoted by Rn, as you know from the calculus course. The two vectors are pairs of numbers, so that each two vector encode one point in the coordinate planes. We can identify R2 with the coordinate plane. The three vectors are just usual vectors in the three-dimensional space, so you can imagine them as some arrows, as physical objects. Now, vectors form matrices. A matrix is a rectangular array of numbers, namely an m by n matrix is an array with m rows and n columns, so that it's an array, a rectangular, with m by n cells. Each cell contains single number. The number which lies in the ith row and jth column is denoted by I sub j. So the first coordinate I, the second coordinate j, and all coordinates took values from 1 to the corresponding sizes, to the number of rows and to the number of columns. The notation, look at the top, I sub j with parentheses, and the limits for the I and for the j are on the top. So the first index I denotes the number, the row number, and the second index j denotes the column number, not vice versa. Examples. For example, look at this formula: I plus j in parentheses, and then, very important to know that I is the first index, so that I is a row index, and j is the second one, so that j is the column index. You see that the matrix has two rows, because I has the limits I to 2, and j has limits 1 to 3, so that the matrix has 3 columns. And the elements which lie on the ith row and jth column is calculated by the formula inside the parentheses I plus j, so that we get the matrix of this form: 2 by 3 matrix consisting of these numbers. Another example: any number is a 1 by 1 number, 1 by 1 matrix. The third example: suppose that matrix B is given by the following formula: you see that, again, this formula gives us a way to calculate each element of the matrix. If you like programming, you can translate this formula to the function that calculates the elements on the ith and jth cell. So that this matrix consists of single row, 4 columns. Each element of this matrix is calculated by the formula G squared. Now, let us consider some special matrices. The row vector is a matrix of 1 by n. The column vector is a matrix n by 1. So each vector, n vector, can be represented by 2 matrices, the row vector and column vector. We will identify the n vectors with the column vectors, so that the Rn for us is the space of the column vectors. It is maybe look like something that doesn't important, but later we'll see that there are some points there, the row vectors and column vectors are not equivalent to each other. Analogously, the set of all m by n matrices is denoted by this R up m by n. So similar to Rn, the set of n vectors. So matrices are two-dimensional. There are 2 dimensions, and another one special matrix is the null or zero matrix, which consists of zeros. Each cell is equal to 0. So for each size m by n, we have one null matrix, which is sometimes denoted by bold 0. So very special matrix is the null matrix. Now let us consider some basic operations which can be applied to matrices. Some of them are arithmetic operations, and some of them are special for matrices, and which can't be applied to numbers, or at least if you apply them to numbers, you doesn't have any new. Now let A be an m by n matrix as before. Remember that this notation means that the first element is A11, the second one is A12, etc. up to m rows and n columns. So the size of A, the size is a kind of operation. It to each matrix it associates the pair of its dimensions, so that the first number is the number of rows, m, and the second number is the number of columns, n. So the size is a pair, m, n. Sometimes we can put m times n. Now, another operation is cutting one row from the matrix. Extracting one row, the ith row is denoted sometimes by a sub I, if the matrix itself is denoted by A. So the ith row is the row vector. Analogously, the j column of A is the column vector, consisting of all elements of this column, so that the row has the length n and the column has height m. Now, one important operation is transposition. The transpose of the matrix, if you have, for example, some matrix, you can just transpose it by this way. So you get from m by n matrix a matrix of the size n by m. The rows and columns are interchanged in the transpose matrix, so it is given by the following formula. The first index in the transpose matrix is j, the second index is I, so that if the original matrix had m rows and n columns, then the transpose will have m columns and n rows. For example, the row vector after transposition gives the column vector, and the column vector gives the row vector. So the two kinds of vector are transposed to each other. Another example. Recall that we have considered the matrix given by this formula. This is just the matrix 2 by 3 matrix 2, 3, 4, 3, 4, 5. Now we have the transpose, which is given by very similar formula, but j and I are interchanged. Then we get the following matrix. From the long matrix we get high matrix. From 2 by 3 we get the matrix of 3 by 2 with the rearranged same elements. So the first column was 2, 3, so then the first row of the transpose matrix will be 2, 3, etc. Each column became now a row, and vice versa. Addition of matrices. Simply to say, matrices are added to each other component-wise. What does it mean? For example, consider two similar matrices. Similar means that they have the same size. One matrix is 2 by 3 and the second one is 2 by 3 again. Then you can add them. Just imagine that you choose one matrix and another one and put one over another one and then add the numbers which are on the same cell, so that you can just add first element to the first one, the second element of the first row to the second element of the first row of the second matrix, etc. So look, you get from these two matrices this one. Formally, let us give a formal definition. If you have two matrices A and B of the same size m by n, you can add only two matrices of the same size. Then the sum is the matrix of the same size C, which is calculated by the following formula. Each element of the matrix C is the sum of two elements of the matrices A and B of the same coordinates I and j. You might ask, why can't we add, for example, two matrices 2 by 3 and 3 by 2? Because the first one has 6 elements and the second one has 6 elements. Why can't we add these matrices one to another one? Because we can't organize the matrix of the result, which could be result 2 by 3 or 3 by 2. There is no good answer to this question. That is why there is a common rule that we can add to each other only matrices of the same size. Similarly, a scaling of a matrix, that is a multiplication of it by a number, is component-wise as well. For example, if you multiply this matrix to the number -2, then you get that matrix. Each cell is multiplied by -2, and all cells are in the order as well. Formally, if A is a matrix of size m by n and alpha is a real number, then alpha A is a matrix C such that C I sub j is obtained from the analogous element of A multiplied by alpha. Using these two operations, multiplication by number and addition, which are called linear operations, you can produce some other operations. For example, the subtraction. Look, in this example on the top, the zero matrix can be obtained from any matrix by multiplying it by 0, and the subtraction is defined or can be defined via the addition and multiplication by a number by the following standard formula. For example, if you subtract this matrix from that matrix, look why and how we get this equality. So the subtraction of matrices is component-wise as well. A multiplication of matrices is a more difficult operation than the previously considered one. It is sometimes close to the neither to the multiplication of numbers, but probably it is close to the scalar product of vectors, because if you multiply two matrices of some sizes, you can get a matrix of another size. Moreover, you can't usually multiply a matrix by itself. Namely, if you have two matrices A and B of size m by n first one and of size n by r the second one, then the product AB is an m by r matrix, so that the first size was m by n, the second n by r, and this number n, the common dimension of two matrices, is omitted in the result, so that the result is m by r. Because in the first matrix you have rows of length n, and in the second matrix B you have columns of high n, so the length of the rows and the length of the columns of the matrix B are equal to each other. Then you can produce a scalar product of a row of the matrix A and of the column of the matrix B. These scalar products organize another array of data. Then this data array is the matrix product A multiplied by B. So the result has the side m by r, and each element of the result is the scalar product of some row of the first matrix and some column of the second matrix. For example, formal definition is the following: C I sub k is calculated as the sum of these elements of two matrices A and B, so that it's a sum of n elements. For example, let us multiply these two matrices. First matrix is 2 by 3, and the second one has a side 3 by 2. Then they could be multiplied, and then you get the following result. The operations with matrices that we introduced shares many properties of standard arithmetic operations. That is why abstract algebra applied to matrices is so useful. Let us consider these properties in details. First, the standard properties of addition of matrices. Of course, here we assume that all these matrices have the same size, both for the first property, which is called commutativity, as well as in the second property, which is called associativity. You see, these are standard properties of summation. Now, the properties which includes the multiplication of matrices by numbers. You see that if you scale a sum of two matrices, then you can separately scale the summons. For example, if you consider the minus sign before the matrices A and B, it is the same then to sum the negation of A and the negation of B. And as well, if you multiply a matrix by a product of two numbers, then you can, of course, multiply first a matrix by one number and then multiply the result by the second one. Now, let us consider the properties that includes the multiplication of matrices. Here we assume that all matrices are compatible, meaning that all products of matrices in both sides exist. For example, if we write A multiplied by B, then the second dimension of the matrix A is equal to the first dimension of the matrix B. So we see that there is a property of associativity of matrix multiplication, as well as the properties of distributivity. That is the property that if you have the sum of A and B multiplied by C, it is the same as multiply A by C and then multiply B by C and then the sum of the results. Similar situation for the left multiplication by C. Well, now we have another kind of associativity of multiplication of one number by two matrices. If you multiply a number by a product, then you can multiply this number by the first term of the product and then multiply by the second term. Or the same result will be if you multiply the number by the second term and then multiply the resulted matrix by the first term from the left. Okay, I said multiplied from the left, but because we'll see later that the multiplication of matrix has no property of commutativity. Okay, but firstly, let us discuss the properties of transposition. The first property is that if you transpose the transposition of A, then you get A itself. People say it in abstract mathematics that the transposition is involution in this, on the set of matrices. Second, if you transpose the sum, you can transpose the sum separately. As well, if you multiply a matrix by a number, then you can transpose it and then you get the result after multiplication by the same number of the transposition of the original multiplied matrix. And then the last property here is a little bit non-standard, because if you transpose the product A multiplied by B, then to calculate it using the transpose of the matrices A and B, you should change the order of the terms, so that first you multiply B and second you multiply it by A. B transposed multiplied by A transposed. It is the same that transposed to A dot B. Okay. As a corollary, you can transpose a long product of 3 matrices, of 4 matrices, of 5 matrices. In all long product, if you transpose the long product, you should change the ordering of the terms by the opposite one. For example, here you see the proof for 3 matrices. If you transpose the product ABC, then you get C transpose multiplied by B transposed and multiplied by A transposed. Okay, this is the same property for a long product of matrices and the rule of transposition of a long product. Okay, now let me say again that generally you can't assume that the product AB is equal to BA. For example, if A and B are rectangular matrices, then AB is not of the same size as BA. You see that if, say, A is m by n and B is n by m, then both products exist, but they have different size, m by m and n by n. Moreover, even if the matrices A and B are square matrices, then both products have the same size. But you see in this simplest example that the product depends on the ordering of the terms. For example, if you multiply the first matrix by the second one, you get again the second matrix, which is non-zero. But if you multiply them on the opposite ordering, then you get zero matrix. So you see in this example that there are non-zero matrices such that their product is zero, in contrast to the standard situation with numbers. which are one-dimensional matrices. Okay. Moreover, there are some special matrices. First special matrices, matrix is the simplest matrix probably, the matrix consisting of all zeros, all elements of the null matrix, which is called also zero matrix, are zeros. In each size, m by n, you have a null matrix which has standard properties of the number 0. If you add any matrix to null matrix, then you get again the original matrix. A plus 0 is A. Moreover, if you multiply null matrix by any matrix, from right or from the left, then you get another null matrix. If A is not square, then this new null matrix will be of other size, but it will be again a null matrix. Another interesting matrix is called the identity matrix. It plays a role of unit on the, with respect to the matrix multiplication. You see that it is not a matrix consisting of all units, but it has ones on the main diagonal and zeros outside the main diagonal, upper and lower than the main diagonal. And the properties of this matrix are the following, and the main property is that if you multiply any matrix by this identity, then you get again that any matrix. A multiplied by I is equal to A, and I multiplied by A is equal to A again. So that that is why I plays the role of unit. The second property is that about multiplication by a number. You see that we have two kinds of multiplications for matrices: multiplication by a matrix and multiplication by a number. In fact, you need only one kind of multiplication. If you want to multiply the matrix A by some number alpha, and maybe you have only one function in your computer system that multiplies matrices by each other, then you can firstly multiply this number by the identity matrix, and then you get the matrix where alpha lies on the main diagonal in each point, and this matrix has zeros outside the main diagonal, and then multiply two matrices. Multiplication of of a number by a matrix is again a multiplication of some matrices. Let me now show you how to use Python for vectors and matrices and for matrix operations. There is a special library in Python which is suitable for matrices and vectors and linear algebra, which is called NumPy. NumPy library. Look at this code. Here the first string imports NumPy, and we denote it later by NP. And then you see NP array. NumPy array is the same as vector. We mathematicians call vectors the thing that programmers often call just a numerical array. That is why in this library vectors are called arrays. So we create a vector consisting of three numbers: 1, 2, 1, 4, 5, and we call it A. And the vector B similarly consists of again three numbers. So these two vectors are three-dimensional, so we can add them to each other, and to write C is A plus B. You can use this code and run it on your computer, for example, and you'll get, if it's okay, you'll get that vector 0, 8, 58. What will happen if we multiply two vectors to each other? We get component-wise multiplication, so that the product star multiplies 1 by -1, 4 by 4, and 5 by 53, the first component of the first vector, and place it onto the first component of the new one, and then the second components, the product is placed on the second component of the new vector, and the same is for third component, so that vector D, which is a product of A and B, will be the vector of that kind. How to multiply, how to get a dot product, you can ask. It is the same. You can use the matrix multiplication, for example, in order to get a dot product, or maybe just dot. The matrix product is denoted by dot but for matrices. Okay, again, a matrix is just something that's called two-dimensional array. That is an array of arrays. So that the first matrix consists of two strings. 1, 4 is the first string, and -5, 8 is the second string. This is the matrix M1. The matrix M2 similarly is of size 2 by 2. It contains two strings, each of two elements, and so you can calculate the sum. M sum is just M1 plus M2. It is the standard sum of two matrices. And then, if you use not the star product, but the special function NP dot, then you get a product of two matrices. So you get this matrix. If you run this code, you get the product of two matrices. Again, by our rule, multiplied by a column, etc. So the standard product of matrices. The null matrix and the identity matrix have a special description on the NumPy, in the NumPy array. So zeros, NumPy zeros is the null matrix. Its shape or size is 2 by 3. It is these 2 and 3 are the list of two arguments. 2 and 3 is the argument of the function zeros. And the identity matrix is defined by the word identity, and here we create an identity matrix of size 3 by 3. Now we discuss one of the main and most common problems of linear algebra. That is the problem of solving a system of linear equations. There is another problem close to this one. From the viewpoint of abstract algebra, there is one lack on the list of matrix operations. There is no division for matrices. We'll try to introduce some kind of division for matrices by introducing an inverse matrix, that is one divided by a matrix, in a sense. These two problems are very close to each other, because if you solve an equation, then a simple equation, you need often a kind of division to find the solution. For example, let us consider a linear equation on two variables. It is called linear because such an equation defines a line on a coordinate plane. X and y are variables, and a, b, c are numbers, parameters. This is a line on the standard coordinate plane, so a line is defined by this equation. This means, you know, that a point lies on a line if and only if its coordinates, x and y, satisfy this equation. Similarly, one can consider a system of such equations. You might consider 2 or 3 or 5 equations, and for example, in the case of 2 equations, the solution of a system of linear equations consists of all common lines, common points of the lines L1 and L2 on the coordinate planes, which where the coordinates are x1 and x2. Don't worry, these coordinates are x and y. For example, if the lines are close to one another, then they have only one common point, which is a solution. But there is a possibility that there is no solution. This means that the lines have no common points, or on the opposite side, that there are a lot of solutions. That is, the graphs of two lines coincide. This means that each point on this common line is a solution of the system of the equation, so we have an infinite number of solutions. These are common situation for systems of linear equations. Generally, a linear equation in n variable is not an equation defining a line, but an equation of the similar form as an equation defining a line. That is, sum of the variables multiplied by some parameters a is equal to some constant. This is a general form of a linear equation in n variables. The set of its solutions is a subset of Rn, so that it is not a line generally, but it is called hyperplane. Because, for example, in the case of three variables, this equation defines as usual plane in our space, in our three-dimensional space R3. Okay, you can shortly write out the same equation as a dot product of two vectors, or as the same as a matrix product of the transpose of the column vector multiplied by the column vector of x's. So this equation has only this short form of four symbols. The vector x is the unknown vector, or a vector on unknowns. It collects all the unknown variables, and the vector a is a constant vector, the vector of parameters. It is again an n-dimensional vector, so it consists of all coefficients a1 and an. And the right-hand side of the equation is again the number b, single number. Okay. The above equation defines a hyperplane. As well as a line divides a plane by two halves, half planes, then as well each hyperplane divides the whole space Rn, but by two half spaces. So to be precise, we get three parts. The first plane part is the hyperplane itself. The second part, the first half space, where the dot product of the vectors and x greater than b. This dot product is the matrix A transpose by x. And the half space 2, or negative half space, if you assume that the first half space is positive, then the negative half space is defined by the condition that this dot product is less than b. So this property is used in some machine learning technique called linear classifier. If you have two clouds of points and you want to separate them by some delimiter, then the simplest way is to find some hyperplane that separates them. And then you can check if and one additional point belongs to one cloud or the second cloud, by just calculating the product of I transpose by the coordinate vector x of this unknown point. If you get the inequality that this product is greater than b, then it belongs to the first cloud. If you get an inequality less than b, then to the second cloud. And if in very rare case then you have the exact equality, then you have no decision. Unfortunately, in this situation the classifier doesn't work, but it is almost impossible for rather general point. Okay, now let us consider a system of several, say, m linear equations. That is a system that defines that an intersection of several hyperplanes. Each equation defines a hyperplane, so you get an intersection of m hyperplanes. If they have a common point, then the system has a solution. Look, the system is defined by a lot of coefficients. Each coefficient has two indices. First index denotes the number of rows, that is the number of equations, and the second coefficient is the second index denotes the number of columns, that is the number of variables. And also, so the coefficients A form a matrix of size m by n, and the coefficients B form a vector of size m. So you can write out the same system in a shorter form. A multiplied by x is equal to b, where A is a matrix. M by n matrix consists of all coefficients A. X is again the vector of unknowns, and b is the m-dimensional vector of the right-hand sides of the equations. So all the data about our system consists of the matrix A and the vector B. It can be rewritten even in a more compact form by encoding all coefficients, including the constant terms on the right-hand sides, organizing them as one single matrix. It will be a matrix of size m by n plus 1, and it is called an extended matrix of a system. So the ith row of this matrix corresponds to the ith equation. The number of columns, if it is less than n plus 1, corresponds to the suitable variable, and the last column corresponds to the constant terms, that is to the right-hand sides. There is a kind of classification of all systems of linear equations with respect to if they have solutions or no. Definite system defines some x's uniquely. That is, a definite system should have a single solution, single vector x satisfying the system. Or, by the other side, the hyperplanes have single common point. Let us recall our illustration with two lines. So the first case, in the two-dimensional case, then all the lines intersect on one point. The second case is the case of the inconsistent system, the system that has no solution. This means that the hyperplanes has no common points. You see in this picture that what happens for two parallel lines. And the third case, the case of indefinite system, that is the system that has some solutions, but it doesn't define uniquely the variables x. This is the case when the system has infinite set of solutions. Note that if a system of linear equations has at least two solutions, then it has infinitely many solutions, because if the set of solutions of the system of linear equation, the set of intersections of hyperplanes contains 2 points, that it should contain also the whole line which includes these 2 points. This property is a part of the definition of the subsets which calls linear variety. Linear variety are such subsets which are sets of solution of some linear equations in n variables, systems of linear equations. N variables, that is, linear varieties, are the intersections of hyperplanes. To solve standard algebraic equations, we usually need some additional operations but summation and multiplication. In particular, we need the division for numbers. As well, if you want to solve a matrix equation, that is a system of linear equations in a matrix form, then we need some additional operations with matrices. Firstly, we would like to create some kind of the division for matrices. To create a division, we introduce new concept, the matrix inverse, that is 1 divided by a matrix. Consider a system in one variable as a toy example. A linear system in one variable of one equation is just an equation x is equal to b, where a, b, x are just numbers. So, if the number a is equal to 0, you can't express x in terms of a and b. The system either has no solutions or arbitrary, each number is a solution. But if a is not 0, then we can simply solve it by dividing b by a, or on other terms, of the multiplication of the inverse of a by b. Okay. Let us now consider a general system in n variables. In a matrix form, you see it looks very close to this equation. Ax is equal to b, but now A is a matrix and x and b are vectors. Suppose that the system has a solution. Moreover, suppose that the system is definite, that is, the solution is unique, as you know. Now, how to find it? Can we apply something similar to that trick? That is, can we find a matrix A power minus 1, something close to the inverse of matrix, such that x is equal to the product of this new matrix by b? Okay, definition. Suppose the matrix A is a square matrix. That is, the both sides coincide and equal to n. A matrix of size n by n, so of the same size as A, is called an inverse of I if the following two equalities hold. That is, if you multiply the inverse by A, both from left or from right, you get the identity matrix. It is close to this to the similar equality for numbers. The one plays the role of the identity matrix. First, why we introduce this notation a power minus 1? If there are, for example, several matrices satisfying both equalities, then it is unclear which one is denoted by a power minus 1. To avoid some misunderstanding, we would like to prove, firstly, the uniqueness of the matrix inverse. That is, we prove that if the inverse of A exists, we don't know if it exists or not, but if it exists, then it is unique. Indeed, suppose that C is another matrix satisfying the both equalities. That is, AC is equal to CA is equal to the same identity matrix, which I denote here by I in place of IN. It is the same. Then look at this chain of equalities. C is equal to Ci because of the property of the identity matrix. I we can extend as a product A multiplied by the inverse of A, by the definition of the inverse. And then you can rearrange the parentheses because of the associativity property. And then you see that inside the first parenthesis is the product Ca, which is equal to identity matrix as well by our assumption. Then we see that because of the property of the identity matrix, that the last matrix is equal to the inverse of A. So C is equal to the inverse of A. By the other words, any other matrix satisfying these equalities is again the same matrix A power minus 1. So the inverse unique, provided that it exists, and this means that we have the right to introduce the notation A power minus 1. Now, let us consider examples. The first example is the negative one. Zero matrix has no inverse. like the number 0, which has no inverse number, because if for each matrix C, 0 multiplied by C is not equal to the identity matrix, it is equal to 0 matrix. Let us introduce the definition. A square matrix is called degenerate or singular if it has no inverse. So 0 matrix is degenerate. In contrast to the case of numbers, there are other degenerate matrices. We'll discuss this later. And a matrix is called non-degenerate or regular or invertible if it has an inverse. So good matrices are non-degenerate or regular. For example, each non-zero number, if you consider it is a number or is a 1-by-1 matrix, it is non-degenerate because it has an inverse. Now, the unit matrix has an inverse, so the unit matrix is regular. The identity multiplied by the identity is equal to the identity, so that the identity is the inverse of itself. Now, there are other matrices which are not identities, but they also has inverses. Look, for example, on the last on the example number 2. You see that the matrix A2, 0, 1, 1, 2, 0, 1 has the inverse 1 minus 2, 0, 1. Just multiply these two matrices from the left or from the right, and you'll, in both cases, get the identity of order 2. So these matrices are inverse to each other. Properties of matrix inverse. So we have a new operation with matrices, maybe with non-degenerate ones, but we'll discuss later how to algorithmically recognize regular matrices. Now let us first study the properties. First one is the inverse to the inverse is the matrix A itself. So taking the inverse is the involutive operations. Again, is an involution, like a transposition of matrices. Second, like the formula for the transposition of a product of two matrices, if you calculate the inverse of a product of two matrices, then it is a product of the inverses with the opposite ordering of the terms. Note that the ordering is the opposite. You can just multiply the left-hand side by the right-hand side, that is AB, AB. If you multiply them by B minus 1, A minus 1, then you'll simply get the identity matrix and vice versa. So if A and B are regular, then their product is regular as well and has an inverse describing about this equality. Now, when a 2-by-2 matrix is regular, you just need to calculate one number. For the matrix A, B, C, D, you need to calculate one number which is called a determinant. We'll discuss them later, but now let us just know that if this number is non-zero, then the matrix inverse exists, and moreover we have a formula for it. Look at this formula. You should divide the matrix by the determinant, so that is why it should be non-zero, and then inside the matrix you change something. You change the elements on the main diagonal by each other, and the two other elements change their signs but not change their places. So this is the formula for the inverse of a 2-by-2 matrix. Now, the next property is very important. If you have a matrix equation of the following form, matrix A multiplied by the matrix X multiplied by the matrix B is equal to C, where X is an unknown matrix. Maybe you have no B, or you can just place the identity in place of B, then you get an equation AX is equal to C. As well, you can place the identities on the place of A, and then you get the identity XB is equal to C. So, indeed, it is this equation includes several cases of matrix division. Suppose that matrices A and B are regular. Then you can divide the both sides of the equation both by A from the left, divide means that you multiply the equality by A from the left, by A inverse from the left, and also you can divide by B by multiplying the whole equality by B from the right, and then you get a formula x is equal to A minus 1, C, B minus 1. In particular, each such an equality has a unique solution x. For example, a system of linear equations is again a particular case of such an equality, where A is a matrix. We put the identity in place of B, so we don't see the matrix B here, but we see that in the right hand side the vector B vector is just a matrix of the with 1. So where tall vector B, tall matrix is a vector. So if A is regular, then the system is definite. Moreover, we have a formula for the solution. The vector x is equal to A minus 1 multiplied by B. That formula that we needed. For example, consider a system of linear equations. If the system is definite, it looks like, because these lines, the first line defined by the first equation and the second line defined by the second equation, looks not parallel. Maybe not. So we have a matrix form of this equation. A matrix multiplied by the vector x1, x2 unknown is equal to another vector b on the right hand side. Then let us try to find the vector x. You write out the formula for the matrix inverse. Firstly, you write the solution of your matrix inverse, and then you use the previous formula for the 2 by 2 matrices. You see that the determinant is the product minus 1 multiplied by 5 minus 3 by 3 is equal to minus 14, so it is non-zero. You can apply the formula and to get the unique solution of the system. The matrix is regular, it has an inverse, and using this inverse we calculate that the unique solution is defined by these values of the coordinates. Now let us look to this code page how to calculate matrix inverse in Python. There is a just function called inv in the NumPy library, NumPy linalg inv. So if A is a matrix, that is array of arrays, 2 by 2 matrix, and B is a right hand side vector, which is defined just as an array of arrays, so we get a vector, a matrix of the size 2 by 1, then inv is the inverse of A. So we can just calculate the unknown vector x as a product of inv by b. If you run this code, then you get the value of x. This is the same system as in the previous example, so you get the numerical values which are approximation for that ratios defining the coordinates of x. We have already discussed a method based on matrix inverse, which allows us to solve some definite systems of linear equations, that is, systems with single solution. Now we can discuss a general method to solve any system of linear equations, even if the system has infinite number of solutions. This method is a classical one, which is called Gaussian elimination. That is a way of elimination of variables named after Gauss, who was the famous mathematician of the world about 200 years ago. Let us consider an example of elimination of variables in a linear system. Consider a system of two linear equations in 3 variables. that is, geometrically you can imagine an intersection of two planes in the three-dimensional space. That is, in the best case, the intersection is the line. And in the worst case, the planes are parallel to each other and there is no solutions. We hope that there is a best case. And so, how to find this line? Let us try to eliminate variables from some equations. For example, let us subtract the first equation multiplied by 2 from the second one. Then we get the next system. You see that the first equation is the same as in the original one, but the second equation now has no x. That is, x in this equation is multiplied by 0. Now, to eliminate y from the first equation, you can subtract the second equation from the first one and then to replace the first equation by this new one. Then you see that you get a system where x presents only in the first equation and y appears only in the second equation. So you can express x in terms of z and y in terms of z, and this is a solution. Z can take any value, an arbitrary value, and then you can calculate the values of x and y in terms of z. So this is the solution of equation, of the system of the equations. So this was our problem, which can be expressed in a matrix form as the extended matrix of the system. So this is the most compact form of collecting all the information about the coefficients of the system. So we have provided several operations with matrix. From the first step, after the first step, you get a matrix that you have 0 in the lower left corner, and then after the second step, you get another matrix such that it has one another 0 on the second cell of the first row, and then for the system corresponding to the last matrix, you can express two variables in terms of another variable z. Okay, let us try to formalize this idea. First, let us think about which kind of operations we can provide with the matrices in such a way that the systems save its set of solutions, so that these operations should transform a system of linear equations to an equivalent system. These operations, or at least the most common of them, are called the elementary row operations. The row of matrices of the matrix A are denoted by A sub 1, A sub 2, etc. A sub 1 is the first row and A sub n is the last nth row. So there are three kinds of elementary operations. You can imagine that these rows correspond to the equations of a system of linear equations. So you can see that all these operations don't change the set of solutions of the system. First operation, just exchanging of two rows. The row J is placed on the ith place, and the row I is placed on the place G. Of course, this is just the interchanging of two equations in the list of the equations, so the list of solutions doesn't change under this operation. Second one is a row multiplication. That is that is a multiplication of one single row of a matrix by a non-zero number. This corresponds to a multiplication of one equation of a system by a non-zero number lambda. So again, this saves the set of solutions. And the third operation is the summation, that is, you add one line row multiplied by lambda to another line, and the result is placed on the place of this another line that is in the ith place. So in this situation, for the system of linear equations, you just multiply one equation by a number and add the result to another equation, and then to put the result to replace this another equation. So you can easily check that all these operations save the set of the solutions of the system of linear equations. And from the other point of view, all these operations provide a way to transform one matrix A to another matrix A prime of the same size, the same number of columns and the same number of rows, but with a little bit changed, so that either one line is changed or the ordering of the lines is changed. Okay. Let us, for example, apply the elementary transformations to the unit matrix, that is, to the identity matrix. The results are called elementary transformation matrices. The first operation replaces two rows of the unit matrix, so you get the matrix of this form, Tij, where all elements outside the main diagonal but these two ones are zeros. All non-expressed elements are zero. Okay, the second transformation, multiplication of a row by a number, corresponds to the following diagonal matrix. All elements outside the main diagonal are zeros, and all elements of the diagonal but the ith one are ones, and the element of on the place I on the main diagonal is equal to lambda. And the elementary transformation matrix of the third kind is the following: the unit matrix plus one single lambda outside the main diagonal. All other elements are zeros. Okay. Theorem. If I prime is a result of one elementary transformation, then this matrix is equal to the matrix I multiplied from the left by the corresponding elementary transformation matrix. For example, of course, if you interchange the two rows of the matrix A, and you have a function which gives you a multiplication of matrices in your computer system, then you can provide this operation by multiplying A from the left by the corresponding elementary transformation matrix Tij. And the same situation for the other transformations. We have met this situation that many matrix operations are expressed in terms of matrix multiplication. As well, the elementary operations are expressed in terms of the matrix multiplication by this theorem. For example, if the matrix A has this form, let us provide an elementary operation of the third kind, and let us add the first row multiplied by -2 to the second one and place the result on the place of the second one. You can easily find that the matrix of the elementary transformation looks as this T, and if you multiply this T by this matrix A, then you get that matrix A prime, which is obtained. It is easy to check that this matrix A prime is indeed obtained by this elementary transformation from the matrix A. If you multiply, for example, on the first column, you should multiply 2 by -2 and add this to 3 and place this in the place of this 3, the lowest element of the first column, and then you see this is -1, etc. if you provide elementary transformations one by one, and you could try to simplify the matrix. For example, this is a matrix of a system of linear equations, and you would like to simplify your system. How simple can you make your matrix? There are two answers to this question. The first answer is that a matrix is said to have a row echelon form if the following two conditions are satisfied. That is, first, all rows of zeros are below all rows with non-zero elements, with some non-zero elements, and also the first non-zero element of each row is, we call such element the leading coefficient of the row. This element should be placed to the right of the leading coefficient of the row above it, so that the row above the leading coefficients look like some kind of sprayers. You will see the examples later. This is a good form of the matrix. It has a lot of zeros, all elements below the leading coefficients and below and left to the leading coefficients. From this direction of any leading coefficients, all elements are zeros. So this matrix has a lot of zeros. Moreover, we can even imagine a canonical form of the matrix, or this form is better than the echelon form. In particular, any canonical form is an echelon form. That it is defined by the following conditions. The first two conditions are the same as in the definition of the echelon form, and there are two other conditions. Third, that the all leading coefficients are equal to 1. And moreover, all entries above leading coefficients, as well as the entries below the leading coefficients, are equal to 0, so that the whole column which contains a leading coefficient should be of the form 0, 0, 0, 1, 0, 0, 0, 0, 0, so that there are a lot of zeros and ones inside a matrix in a canonical form. For example, the first example is the example of a row echelon form. You see that indeed there is a kind of straights, and all zeros are below, and all elements are to the left and to the bottom of the leading coefficients are zeros, and all zero rows are below non-zero ones. And here you see also the examples of canonical forms. The canonical forms are also echelon forms. So all these are examples of the echelon forms, but in the canonical form you see that the leading coefficients are ones. Look at the first example of the canonical form. And all elements but these ones with the lead of the row of the columns containing leading coefficients are zeros, and all other columns are just inside these straights, so that the coefficients are really leading. For example, the zero matrix as well as the identity matrix are in the canonical form. Theorem. Why this echelon form and the canonical form are so important? Theorem said that each matrix can be transformed with a sequence of elementary operations to another matrix which has a canonical form. In particular, this matrix B has a row echelon form. Moreover, such a canonical form is unique for each A, so it is uniquely defined by A and doesn't depend on which kinds of elementary transformation you choose. You can get the same canonical form by a different chains of elementary transformation, but the result will be the same if it is a canonical form. In some problem, you will need just an echelon form, so you need a low number of elementary operations to reach the row echelon form, but the canonical form is much better than the one. For example, let us recall what we have done in this system of linear equations that we have solved previously. In fact, we operated with the matrix of this system by elementary transformation. The first elementary transformation, the subtraction of the first row multiplied by 2 from the second one, and the second elementary transformation is the subtraction of the second row from the first one. Then you see that we get a matrix in the canonical form. So this was really the Gaussian elimination method applied to our system of linear equations. We have considered examples of elimination of variables using elementary transformation. Let us now discuss a formal algorithm which for any matrix gives a way to find the elementary transformations leading this matrix to its canonical form. Okay, Gaussian elimination algorithm. The problem which is solved by this algorithm: if a transformation of an arbitrary matrix A to its canonical form. So let us assume that for each step we deal with single column of the matrix. If the first column consists of zeros, then it is the column which can be used in the canonical form. Then we assume that this column, that this is all is okay with this column, and then we use deal with the second column, then with the third column, etc. So that suppose that after a few such steps we found the first column of the matrix A, say the column number J, which differs from the canonical form, from a possible canonical form of the matrix. This means that all columns with numbers less than J are on the canonical form, so that they are either contains leading coefficients, and then these columns consist of one unit elements and all other elements zeros, and or they has no leading coefficients, so that all non-zero elements of these columns are toward the right of some leading coefficients of the columns with less numbers. Now, the algorithm consists of 5 steps which we apply to each such a column. Find first column which doesn't correspond to a canonical form. If such a column doesn't exist, this means that matrix A has reached its canonical form, so that we have done. Now, the second step, if such a column exists, find the first row of A such that there exist of all the leading coefficients of all previously preceded rows, so that there are some rows which are toward the left of our rows, some columns which are toward the left of our columns, and these columns, some of them, contain leading coefficients. All these leading coefficients lie in some rows, 1, 2, up to some number I minus 1. So now we'll deal with the row number I. Okay, now if the element Ij, which lies or in our column, in the intersection of this column with the ith row, if this element is non-zero, is 0, then let us switch this element with some other elements of this column which is non-zero. Switch by switching 2 rows. This is an elementary transformation. Indeed, we assume that our column doesn't satisfy the condition of the canonical form. This means that it has a non-zero element below the previously constructed rows which contain leading coefficients. So this means that there is at least one non-zero coefficient in this column number J. Moreover, we can assume that this non-zero coefficient lies below the previously constructed rows. That is, its I coordinate is equal to I or greater. So that after one elementary transformation, we can reach the situation where the element Aij is non-zero. Then the next step is to multiply the row I by the inverse of this non-zero coefficient. Then, after this multiplication, we get the coefficient Aij equal to 1 in the new matrix. Now, we have a new leading coefficient of the row I equal to 1. Then, to get the canonical form of the column J, we just subtract the ith row from each row with AT with number t non-equal to I, multiplied before subtracting, we multiply the row I by the element lying in the column J in the tth place. So if we multiply ATI by the row AI and subtract the result from the row A number t, then you get the element ATJ equal to 0 after this subtraction. This means that we get single leading element and all other 0 elements in the column J. Now we proceed with the next column. After applying with these elementary transformations, we get, after at most n steps, where n is the number of columns, the row echelon form of the matrix A. Of course, there are modifications. This algorithm, for example, you can omit some operations if you need to construct a row echelon form only, not a canonical form. Before considering an example, let us discuss what we will see after reaching a row echelon form of the matrix A. For example, suppose we are solving a system of linear equation Ax is equal to b, and let A tilde is the extended matrix of the system, that is AB, and let C tilde is the row echelon form of the matrix A tilde. Here, a submatrix C inside this long matrix is an echelon form of the matrix A, because if you apply elementary transformation to the matrix A tilde, then its submatrix A is transformed by these elementary operations as well. Then the new system, which is equivalent to the original one, is the system with the matrix C in the canonical form. The system is Cx is equal to B prime. Now we have the following proposition. Suppose that the matrix C has R non-zero rows, so that this echelon form has a straight of length R. First, we can easily see if the system is consistent or it is consistent. If this new system contains an equality of the form 0 is equal to non-zero, then it is inconsistent. This means that the element of the new right-hand side vector b prime, the element number r plus 1 is non-zero. Then the system is consistent. And if this element is 0, then the system is consistent, if it is definite or not. Again, we can easily check this. If the number r of non-zero rows is equal to n, the number of variables, then the system is definite. Otherwise, the system is indefinite. So that it is indefinite if this element b prime r plus 1 is 0, and in addition, that the number of non-zero rows is less than the number of variables n. Okay, let us consider an example. Suppose we want to solve this more or less large system of linear equations. Let us organize the extended matrix of the system and apply the Gaussian procedure. In the first step, we subtract the first row multiplied by some elements from other rows in order to obtain all but one zeros in the first column. Now we subtract the second rows from the rows below it in order to obtain zeros in the second column. Then we make the same procedure with the third row. That is, we subtract the third row, multiply by -1, that is, add the third row, to the fourth row. Now we see that in this row echelon form, we have an equation. The last row corresponds to the equation 0 is equal to 32. By the other words, this means that the right-hand side vector has length, the number of non-zero rows of the matrix C plus 1. That is, the system is consistent. Okay. How to solve a linear system using Gaussian elimination? Suppose now that we have reached the canonical form of the extended matrix A tilde. So that C is, it's a matrix C, is the canonical form of the matrix A. How to solve this new system, which is equivalent to original now? Of course, the problem is much simpler. Okay. Solution. Suppose that R, again, is the number of non-zero rows of C. Suppose that the system is definite. We know how to recognize indefinite system. Now, let us separate all variables into two parts. The first part consists of so-called principal variables, the numbers of these variables corresponding to the numbers of columns containing leading coefficients of the matrix C. And all other variables are free. We will assign arbitrary values to free variables, and we will try to express the principal variables using these free ones. Consider, for example, this system of linear equations. We have many equations and less number of variables. What happens now? We apply the Gaussian elimination algorithm. You can check by yourself which kind of elementary operations are applied here. Switching the rows and then subtracting one row from another one, and then again and again. And we get the following canonical form of the system. We write it as a system of linear equations. We see now that one variable is expressed, the variable x1 is expressed in terms of x3, and the variable x2 is also expressed in terms of x3. So that we can say that the variable x3 is free, because the column number 3 doesn't contain leading coefficients, and the variables 1 and 2 are principal, because the columns number 1 and 2 contain the leading coefficients. So that we get the expression of the variables x1 and x2 in terms of x3. One can apply Gaussian elimination to solutions of a number of matrix problems. For example, one can even find the inverse matrix using Gaussian elimination. First, a little theory. Suppose we know a canonical form of the square matrix A. Then we know if it is degenerate or non-degenerate. Indeed, the matrix is non-degenerate, that is regular, that is invertible, if and only if its canonical form is just the identity matrix. That is, the canonical form has n non-zero rows. If the number of non-zero rows is less, then it is degenerate. Moreover, in this case, we have a way to find its matrix inverse. Suppose B is a matrix consisting of two submatrices, A and the identity matrix. Let us apply the elementary transformations to B such that B leads its canonical form. Its submatrix A under this transformation also reaches its canonical form, that is the identity matrix. Then the second submatrix, the right-hand side submatrix, will be the matrix inverse of A. It is not difficult to prove this. For example, we know that if a matrix is non-degenerate, then each system of linear equations with the matrix A has a unique solution, because this unique solution is expressed in terms of the matrix inverse of A. So that in the definite system of linear equations, the canonical form of A should has n non-zero rows. This was a theorem about the definite systems and Gaussian eliminations. So if it has n non-zero rows and it is square, it is square, then it should be the identity matrix. It has leading coefficients in each row. So, reversely, if the canonical form of A is the identity, then there is a sequence of elementary transformations which goes from A to this identity matrix. If T is a product of the elementary transformation matrices, then T multiplied by A is equal to the identity matrix. So, the product of the elementary transformations is the non-degenerate matrix, because it has the inverse matrix, and from this equality you see that A is the inverse of T. By the other words, T is the inverse of A. Now, if it is the case, then the canonical form of A is just T multiplied by A. And if you apply the same elementary transformation to the whole matrix B consisting of two parts A and In, then you apply this elementary transformation to the left hand side A and to the right hand side I. Then in the left hand side you get I, the canonical form, and in the right hand side you get the T multiplied by the identity matrix, that is T, that is the matrix inverse of A. This is the sketch of the proof of this proposition. Let us consider an example. Let us try, for example, to find the matrix inverse for the matrix A given by this form. This is a square matrix of order 3. So we use the Gaussian elimination applied to the matrix B. After the constructing the canonical form of the matrix B, we will see if matrix A is degenerate. If it is degenerate, then we will see that its canonical form toward the left of the bar contains a zero row. If it is not degenerate, then the canonical form should be the identity matrix, so that in the right hand side, to the right of the bar, we will find the matrix inverse of A. Look, the sequence of elementary transformations which leads, after a few steps, to the matrix which has left half equal to the identity matrix. It follows that the right half is the matrix inverse. So we write the answer, the matrix inverse of A is this matrix. The Gaussian elimination method is useful also in connection with another method of solving linear equations. If it is based on so-called LU decomposition. LU decomposition is one of a lot of possible decompositions of matrices as a product of several matrices of simpler form. The LU decomposition in particular is useful for other methods of solving linear equations used in real computation systems, including, for example, the NumPy library. First of all, let us recall what is a triangular matrices. For example, a matrix is called lower triangular if all its elements are concentrated on the main diagonal and below, so that all elements upper the main diagonal are zeros. For example, the identity matrix and the zero matrix are triangular matrix, as well as all other diagonal matrices. Moreover, the elementary transformation matrix of the third type is lower triangular matrix, provided that it adds to some row I the row j multiplied by some lambda if j is less than I, so that you add some string with a small number to a string with greater number, and the first string might be multiplied by some lambda. Okay, similarly, one can define upper triangular matrices by assuming that the matrix is upper triangular if all its non-zero elements are concentrated on the main diagonal or above it, and all elements below are zeros. As well, the identity matrix and the zero matrix are upper triangular matrices, but also some matrices which are familiar for us, also upper triangular, such as the square matrices in a row echelon form, because the leading coefficients of the row echelon form are concentrated either on the main diagonal or above it, and all other elements are concentrated to the right or above the leading elements, so that all the row echelon form is concentrated on the upper triangle of the matrix, including maybe the main diagonal. Okay. The main property of the triangular matrices is the following. If you multiply two triangular matrices of the same kind, for example, two upper triangular matrices or two lower triangular matrices, then you get a triangular matrix of the same kind. Moreover, it is easy to calculate the main diagonal of the result. All the elements of this main diagonal are just products of the corresponding elements of the terms. The first element is a product of the first elements of the main diagonals of A and B, etc. Okay. As well, the inverse of the upper triangular matrix is again an upper triangular, and the same situation with the lower triangular matrices. This means that if you multiply some matrices, then you don't leave the set of upper triangular matrices, say. You multiply upper triangular, they get again upper triangular, you can multiply or divide it by each other, and then you are within the set of the upper triangular matrices. But probably the most interesting application, at least now, of triangular matrices, now for us, this is the most interesting application. This is, look at the example of multiplication, but for the most interesting application is that if you, what happens if you multiply a lower triangular matrix by an upper triangular matrix? What kind of matrices can you obtain in this multiplication? Surprisingly, almost all matrices can be obtained. In fact, suppose that a matrix I is a little bit more than non-degenerate. It is non-degenerate, and also all its upper left upper corner square submatrices are non-degenerate as well. If you have a random matrix, then it should satisfy these conditions. And moreover, many matrices which appear in real life do satisfy these conditions as well. Then there is a decomposition of the matrix A as a product of lower triangular matrix L and an upper triangular matrix U. That is why it's called LU decomposition. Moreover, there are some additional restrictions. For example, you can also assume that the matrix L has only unit elements on its main diagonal. Or moreover, in this situation, you also can assume that U is a row echelon form of the matrix A, so that we can construct at least 1/2 of this decomposition using Gaussian elimination method. But this is not an arbitrary row echelon form, but this is a row echelon form which is obtained from A by using only the elementary transformation of the third kind, where you add or subtract a row to the row below it. And the first row might be multiplied by some lambdas. For example, consider the simple matrix A 1, 2, 3, 4 organized as 2 by 2 matrix. It can be transformed into the row echelon form by only one step. That is, one can provide an elementary transformation which subtracts triple first row from the second one. Then you get this matrix in the row echelon form that we can denote by U. It is the matrix of the elementary transformation is this matrix T. Look, by the previously known our example, this matrix is lower triangular. Now we have that U is equal to this matrix of elementary transformation multiplied by A, so that we can express A as L multiplied by U, where L is the inverse of T, so that this is the inverse of the matrix of elementary transformation. That is the matrix of the inverse transformation. The original transformation subtracts triple first row from the second one, while the inverse transformation adds the triple first row to the second one, so that we have found both L and U. Generally, to apply this method, we might need a chain of elementary transformations which leads from A to U, so that here the matrix T will be a product of the matrices of elementary transformation, and the matrix L will be the inverse of the matrix T. But if all these matrices of elementary transformation are lower triangular, then the product is lower triangular as well, and then the matrix L is lower triangular as the inverse of this lower triangular matrix. So that we'll construct the LU decomposition. There is another useful method to construct LU decomposition. In fact, there are a lot of algorithms, at least several ones, but let us concentrate on one where we can understand now that we can find the LU decomposition without Gaussian elimination, so that this method can replace Gaussian elimination for solution of systems of linear equations. Look at this problem. Find the LU decomposition of this matrix. It is not upper triangular or lower triangular. Let us just denote the unknown elements of the matrices L and U by some letters. They will be variables. So in the matrix L, because we assume that it has units on the main diagonal, there are 3 variables and 6 variables inside the matrix U. And we have one matrix equation, LU is equal to A. Because A has 9 cells, we have 9 equations for 9 variables organized as a linear system. this is the matrix equation. If you multiply L and U, you get that result, this result on the left-hand side. And then you can consider this as a system of linear equation. For example, the first cell is x on the left-hand side as 1 on the right-hand side. So you deduce that x is equal to 1. Then as well, y is equal to 0, z is equal to 1. Now, the next cell is a multiplied by x in the left-hand side, in the right-hand side, you get 0. So you deduce a multiplied by x is 0, x is known to be 1, so that we find a is equal to 0. Similarly, t plus ay is equal to 2, so that t is equal to 2, and now we find u, b, subsequently c, and then finally v. So we have found all 9 variables. So with that we have found the both matrices L and U. You see that this system of linear equations is organized in the following way, that we don't need Gaussian elimination to solve it. This system, in fact, if you write its matrix, you'll see that this is already on the row echelon form, so that you can find the variable x, then to find the variable y, then to find variable z. We don't need elimination of variables, so that this system can be solved relatively easy. Of course, there are another methods of finding LU decomposition, but most general of them finds an analogy of the LU decomposition for an arbitrary matrix, even for a degenerate one. This most general form of it is called PLU decomposition, PLU decomposition. So that here again L is a low triangular matrix. It might be chosen to be with unit diagonal elements. U is an upper triangular matrix. And P is a matrix obtained from the identity matrix by a permutation of columns. So that P consists of the same column as the identity matrix, one unit element and a lot of zeros elements in each column, but these columns are not on the right order, might be. Okay, then such a decomposition can be used for solving linear systems. This is an example of PLU decomposition for such a matrix A. You see that it doesn't satisfy the condition that all its left upper submatrices are non-degenerate. The first such a submatrix of size 1 is just number 0, so that it is degenerate. That is why such a matrix has no LU decomposition, but it has a PLU decomposition. You see that the matrix P is just a 2x2 identity matrix with interchanged columns, and the matrix L is just an identity matrix. The identity matrix is, of course, a low triangular. So, how to use the PLU decomposition for solving of linear system? Suppose you have constructed the PLU decomposition of the matrix A of the system AX is equal to B of a linear equation. So that there are analogues for rectangular matrix, but you can assume that it is square matrix. So you can solve 3 systems. First of all, PZ is equal to B. Then your second system, LU is equal to Z. The third system is UX is equal to Y, so that Z is found from the first system. Then you can solve the second one, then you can solve the third one. All these systems are relatively easy to solve because, for example, PLU, P is just such a matrix that the first system looks like for example, Z1 is equal to B2 or Z1 is equal to B5, etc. So this is not a system but just a list of values of Z. The second and the third systems are in the triangular forms, so that you can find one variable from, for example, from the system LU is equal to Z. Imagine the matrix L, which is upper triangular with units on the main diagonal. So the first equation is just y number 1 is equal to z number 1. The second equation allows us now to express u number 2 in terms of y number 2 in terms of y number 1, etc. So they can at most approximately n square arithmetic operations solve this system. The similar situation with the third system, again it is in its triangular form, so that it is relatively easy and quick method of solving linear equations, system of linear equations, provided that you know the PLU decomposition. Now, how to find it? Of course, we can. So there are a lot of algorithms. You can look at some literature, of course, but in practice, you can just use known functions for it. For example, in our NumPy library, NP here means NumPy. We imported NumPy as NP, so that let B be a matrix. You see the strings of B 001, 022, 3, 4, and then the function LU is just calculate P, L, and U for this matrix B. This PLU decomposition can be checked by multiplying. You see that inside the function np all close, you multiply first pln, and the result is multiplied by u, and then the function all close check if the result is close to b up to some rounding of decimal points, because the Python use some more advanced algorithm than this integer numbers algorithm based on only integer arithmetics. Then the result may be equal to b up to rounding. So the function all close check if the results are close up to some small decimal, up to some small difference depending on the number of decimal digits. So that, okay, if you try to check this, you will see that it is approximately b. So b from the viewpoint of programmers and practical computations.
Today we will discuss some fundamental notions from linear algebra, namely vector or linear spaces, linear dependence and independence, the notion of basis, and then we will come to the notion of rank of a matrix. And we will apply this notion of a rank to discuss the so-called rank decomposition. For example, we could present a matrix of size 4 by 4 as a product of two smaller matrices. First is just a column, the second is just a row. And we will discuss what this dependent elements here means. And by the end of this week, we will apply this to processing or compressing the scanned document. And before this, we will discuss the properties of the systems of linear equations and how the solution set of homogeneous and inhomogeneous system of linear algebraic equations looks like. So this week, in some sense, is a core part of our course.
Abstract vector spaces. This is the first lesson of the third theme of our course. And up to now, we have studied a number of various classes of mathematical objects, such as vectors, matrices. If you took calculus courses, you have studied also sequences, functions, especially continuous functions and differentiable functions. And now we can make one deep observation. That is, all these various mathematical objects allow arithmetic operations of very similar properties. Why this simple observation is so important? Firstly, one can use the same properties of these arithmetic operations in different situations. For example, if you know that you can rearrange sums in a long sum, then you can apply this property for numbers as well as for vectors and matrices, and also for polynomials, say, or other functions. Second, one can use this fact to program or some operators or long operations. For example, if you would like to implement the sum operation, which calculates the sum of a list of some objects, then you can rearrange sums in a long sum in vectors and matrices, so you can apply a for loop from 1 to n or from n to 1 if you would like to sum n matrices or n vectors or so on. And the most important, the third point, is that you can apply one part of mathematics to another part. We'll see that one can consider n vectors as a kind of model which models many other parts of mathematics, some properties of polynomials, some of matrices, and of course this property will be applied to machine learning and data analysis and so on. This is a very important point which is expressed in the notion of vector space, or so to say abstract vector space. So we would like to apply abstract algebra to study n vectors and matrices and more general classes of objects. What kind of arithmetic operations will be used here? These are the most important and the most common operations. Among them there are addition. Of course, this is the most common operations, but there is no multiplication in all its generality, because a multiplication of two vectors doesn't give a vector, but just a number, so that good multiplication should give a subject of the same kind. That is why the second operation will be scaling, that is, a multiplication of a matrix by a number, or of a vector by a number, or of a polynomial by a number, or some set of data by a number. That is, the second operation is scaling. The multiplication of one vector to another one is not good. And the division is not good too, because there is no good way in general to divide one vector by another one. So, abstract vector spaces. Informal definition is that a vector space is a set of elements of some kind, abstract mathematical elements, which can be added to each other and multiplied by numbers, that is, they can be scaled. Informally, this is the definition, but we can't use this definition to any mathematical theorem or practical problems and so on. To use it, we need some kind of formal, boring part of the definition, boring but very important one. So, a formal definition is the following. Consider some set V because it's called vector space, of some elements which can be expressed by simple numbers x, y, etc., but usually they are bold letters. We call elements of vector space as vectors. That is why it is vector space. Some people also call vector space linear space. It is the same, linear space or vector space. And we assume that for any two vectors, for any two abstract vectors, elements of V, there exists a sum z in the same set, vector space. So if you add, for example, one crocodile to another crocodile and you obtain a pair of crocodiles, it's not a vector space, the set of crocodiles. So, and also for each x vector and each real number, one can scale x by this real number alpha, and then you can obtain the product alpha multiplied by x, and it must be a vector of the same kind, an element of the same vector space. So this set V is closed under two operations: plus and scaling, or scalar multiplication, or product by number. Okay, but it is not the end of the definition. The most important part of the definition is the list of axioms. These two operations should satisfy some axioms. What is the origin of the axioms? Recall that we have considered n vectors, and we know a number of properties of this vector. It is not bad to say that the axioms of a vector space are all common properties of the spaces of n vectors for all n. If the property of n vectors doesn't depend on n, then it should be satisfied in an abstract vector space. More precise, the first set of axioms is the list of 4 axioms of the addition. Look, first axiom is the usual commutativity axiom. X plus y is the same as y plus x for each vectors x and y. Of course, these are standard properties of numbers, of vectors, and of matrices. And if you know how to add, for example, two sequences to each other, then you know that this property is satisfied by the addition of sequences as well. The second one is the property called associativity. It is a property of parentheses. You can rearrange summands by the first property, and also you can rearrange parentheses in a long sum. Associativity. The third property is maybe the most important, because this is the only property that guarantees that a vector space contains at least one element. This one element, which should be in every vector space, is called null vector, or just null, or null element, or some people call it zero vector. It is defined by a property that if you add any vector to null, then you get this original vector for each vector x. And also, the fourth property guarantees that there is not only addition but also a subtraction. Indeed, for each x you can subtract x from 0 and obtain something that's called additive inverse, that is an opposite vector. The opposite vector is denoted by minus x, and it is defined by the property that x plus that minus x should be null vector. Okay, note that there is no scaling in these 4 axioms. Scaling is described by the next list of 4 axioms, so totally we have 8 axioms of vector space. First property of scaling is probably the most natural one. If you scale something by 1, you get the same something, so scaling by 1 doesn't do anything. Also, the associativity of multiplication, the property number 6, and 2 other properties are called distributivity. Distributivity is this property of uniting some common summands as one product. All these properties are standard for numbers, and of course we all know that n vectors do satisfy these properties. How to use this property? Note that the elements of an abstract vector space are called abstract vectors. Note that, for example, n by m matrices form an abstract vector space. So in this context, you can also call matrices as abstract vectors, and you also can refer to, for example, sequences as abstract vectors. You call row vectors abstract vectors and column vectors abstract vectors, and so on. And for all these things, if you deduce something from the axioms, then it is true for all of them. For example, the first proposition and the first example of using this axiom. Proposition. If you scale something by 0, you get the null vector. And if you scale something by -1, you get the opposite vector. How to prove this? So, these are our 8 axioms. We use them to prove the following. Firstly, we want to prove that if f is a vector from V, then 0 multiplied by x is equal to null vector. I will denote here in the bot null vector by null with arrow to distinguish it from 0. Okay. How to prove this using these axioms? First, we write 0x plus 0x. Let us rearrange this using axiom 7. 0 plus 0 multiplied by x. Just because 0 plus 0 is 0, we have another 0x on the right hand side. Now we want to subtract 1 0x from left and 1 0x from the right in order to obtain this. To use subtraction, we need minus x, or here we use minus 0x. Let us write minus 0x, both on the left hand side and on the right hand side. Minus, this is minus 0x. Okay. Then we want to use this axiom, but here we can't use it because we should firstly rearrange the parentheses by using axiom 2. We have by 2, I mean axiom 2, 0x plus 0x minus 0x is equal to 0x minus 0x. 0x minus 0x, x is exactly the same thing, but with replacement of x by 0x. So we can use axiom 4 in order to obtain 0x plus 0 vector is equal to 0 vector. Null vector. So because 0x plus null using axiom 3 is equal to 0x, then we have done what we need. By 3 we have what we need. 0x is equal to 0 vector. Okay, this was the first part of the proposition. Let us now prove another part. We want to prove that minus x is equal to minus 1 multiplied by x. It is natural, but we should prove this. Okay, again, if we have minus x, minus 1 multiplied by x, let us try to plus x. Then we have, by the axiom 5, x is the same as 1 multiplied by x. X here, I just forgot it, x here. So now we can again rearrange the summands by axiom 7. We have minus 1 plus 1 multiplied by x, so it is equal to 0x, or as we have proved, we get 0 vector. Now this is equal to 0 vector. And also x plus minus x using axiom 4 is also 0 vector. How to use this fact? Let us subtract x from both sides of this equation, from this one and from that one. Minus 1 x plus x minus x is equal to 0 minus x. Rearranging summands, the summands by axiom 2, we obtain minus x plus x minus x is equal to 0 minus x is the same as just minus x because of the axiom 3. Using also axiom 3, we get minus x on the right hand side. So minus x plus, again by axiom 4, this is just 0 vector is equal to minus x, and by axiom 3 we conclude that minus 1 x is equal to minus x. So we have proved our first proposition about properties of all vector spaces. Now let us consider examples of vector spaces. There are a lot of examples of vector spaces. First and the most natural one is the real line. It is a vector space with respect to standard operations, plus and multiplication. Suppose x is a number, we consider it as a vector, and let y be another number. Y, what is x plus y? We just add the arrow equal to x after y, and then to get another number called x plus y. So this long white vector. Of course, if you want to multiply a number by a number, you may consider this as a multiplication of a vector by a number. For example, this vector x might be multiplied by, say, minus 2, and you get another vector minus 2 multiplied by x. You can easily check that all 8 axioms are satisfied. The next example should be the first one, because this is 0 example number 0. It is just 0 vector space. It consists on a single symbol, 0 vector. Or you may imagine it as a set consisting of 1 point. The only multiplication at summation table is the following: 0 plus 0 is equal to 0, and 0 multiplied by any number is equal to, again, 0 vector. So you may easily check that all axioms are just the equalities 0 is equal to 0, because there is no other vectors. So it's a trivial example. Let us give a less trivial one. Let it be example number 2. That is the plane R2. Plane R2. You have the coordinate plane r square, and of course, if you have two vectors, say the vector u equal to xy, and the vector, say, v equal to, say, x prime y prime, two coordinates. First coordinates are x and the second ones are y, then the sum of two vectors is just a vector which is the diagonal of this parallelogram. This is 0, and this is the end of the parallelogram. You can identify this point with the vector u plus v. That is the vector x plus x prime, y plus y prime. And of course, if the vector u is multiplied by some alpha, again let alpha be negative, that is alpha u is equal to alpha x, alpha y. Okay, similarly, you can consider any plane as a vector space. Any plane. Let us fix any point and call it the origin. And then for any two vectors on the plane, u, v, you can again construct the same parallelogram and to construct the vector u plus v. And again, you may construct the vector alpha multiplied by u, assuming that it lies on the same line as u and have the distance from the origin equal to alpha multiplied by the length of u up to the sign of alpha. Okay, this is example number 3. Example number 4, let it be the main examples, that is the vector space Rn. All Rn, of course, this is a vector space. Recall that it consists of the tuples of n numbers. I put arrow for vector and no arrow for numbers. So this is a vector from Rn, and you know that there are addition and multiplication by alpha, addition of two vectors. And of course, all these properties called axioms are satisfied because this was the origin of our axioms. All these axioms are standard properties of vectors from Rn. Now let us consider something less trivial. For example, recall that we have considered systems of linear equations. Let this be a homogeneous system of linear equations. That is, it has zero vector on the right hand side. Suppose that A is m by n, so that the unknown vector x is an element of Rn. Let S be the set of all solutions. Set of solutions of these systems of linear equations. That is, S is a subset of Rn. Then I claim that S is a vector space. Indeed, for each two solutions, for example, if x and x prime are solutions of this system of linear equations, then x and x prime are elements of S, then A multiplied by x plus x prime is equal to ax plus ax prime is equal to 0 vector plus 0 vector, so that it is 0. This means that x plus x prime, this vector, again belongs to S. Moreover, if you multiply x by some number alpha, then you again get another solution of the same system of linear equations, because if you multiply x by alpha here, you just multiply alpha 0 by alpha here, so you again get the equality, because you can rearrange alpha as a first summand, and then you get alpha multiplied by ax is equal to 0. But this is 0, so that this is an equation. This means that the vector alpha x is again a solution. So that here the set S is closed under two operations: summation of two vectors and multiplication by a number. This means that it is a vector space itself. We'll prove this after a few minutes. We have seen that some subsets of a vector space could be a vector space as well. This gives us a lot of examples of new vector spaces. To formalize it, let us call a subset of a vector space subspace if, first, it contains the null vector, second, it contains a sum of each two elements of it, and also each contains each scaling of each vectors from each by any real number. That is, for it should be non-empty set. Also, for any two elements of it, its sum should belong to it, and also for any two elements which are vector and a real number, the product of a vector and a real number should belong to this subspace as well. The main property of the subspace is the next proposition. That each subspace is also a vector space with the same operations plus and scaling. So the concept of subspace gives us indeed new examples of small vector spaces inside a large one. But how to check if a subset is a subspace? To check this, we introduce new concept of linear combination. Linear combination is just an element which can be obtained from a given list of vectors by using linear operations, which are sum and scaling. If you scale these n vectors x1, xn by some alphas and then sum the results, then you obtain something new. And of course, this new element should be an element of the same vector space which contains x1, x2 and up to xn, because each vector space is closed under these two operations. So each linear combination should belong to the same vector space. Now, let us define the span of a set Fx of vectors as the set of all linear combinations of these vectors. For empty set X, we define the span as just one null vector. So the null is the linear combination of an empty set. But for other sets of vectors, as well as for null, any span of any set is a subspace. Indeed, look at the definition of the span of X. It consists of all linear combinations of some x1, xn. And if you, for example, scale a linear combination by some number alpha, then you get another linear combination. And also, if you add one linear combination to another one, then you get a third linear combination. So, the set of linear combinations is closed under both operations. And also, the null vector is just a linear combination of x's with zero coefficients. So, the span is indeed a subspace. Moreover, every subspace which contains X should also contain all linear combinations of X, because every subspace is closed under linear combinations as every vector space. So, the span of X is the minimal subspace which contains X. This gives us a way to describe many subspaces in many spaces. So linear combinations are an important part of vector spaces, because given a finite set of vectors, one can obtain an infinite number of linear combinations. Let us discuss them in details. The trivial linear combination is the linear combination with zero coefficients. So the trivial linear combination should be equal to null vector. All other linear combinations are called non-trivial. So a non-trivial linear combination should have at least one non-zero coefficient. If you have one non-zero coefficient or two non-zero coefficients or more, then this is a non-trivial combination. If this is an empty combination, so no summons, or if all coefficients are zero, then this is a trivial combination. Now, an important definition is that a set X is called linearly independent if all non-trivial linear combinations in X are non-zero. So, look, if a set X is linear dependent, then there is some non-trivial combination which gives us a null vector. But for non-trivial linear combinations of linearly independent set, we get new and new vectors. For linearly independent set, all linear combinations with different coefficients give different vectors. So a linearly independent set is the most effective instrument to get many vectors which are not equal to each other. If you multiply them by non-zero elements, you get non-zero vectors. The main lemma about linear dependence, it is very easy lemma. We will prove it in the next slide. So the main property of a linearly dependent vectors is that a set is linearly dependent if and only if one of these vectors can be expressed in terms of other ones. That is, the set is linearly dependent if and only if one of the vectors of this set is equal to a linear combination of the rest vectors. In other terms, a set is linearly independent if no one of these vectors can be expressed in terms of other ones. How to prove this? It is not very difficult. If, say, one of n vectors is equal to a linear combination of other vectors, for example, xn is equal to this linear combination, then one can get a linear dependence. Indeed, one can subtract x sub n from the both parts of this equality. Then you get something which is equal to 0. In the left-hand side, you get a linear combination of these vectors x1, x2 and x sub n. And this linear combination is non-trivial, because at least one of these coefficients, the last one, is equal to -1. So this coefficient is non-zero. Then this combination is non-trivial, but it is equal to null vector. So these elements are linearly dependent. The opposite implication. Suppose now that there is a linear dependence among these vectors. If this is indeed a linear dependence, then in the left-hand side you see a non-trivial linear combination. This means that at least one coefficient should be non-zero. Suppose that this is beta sub n. Then you can express x sub n in terms of other elements by, again, subtracting beta sub n multiplied by x sub n from the both sides, and then dividing this by this non-zero number beta sub n. you see that xn is equal to the linear combination of other elements. We don't know if this linear combination trivial or non-trivial, but we see that this is indeed a linear combination of other elements which is equal to x sub n. This means that the set is linearly dependent in the second sense. We proved the lemma. An important corollary. Suppose that the set X spans some vector space L. Of course, L as a span is a subspace of the vector space V, and then you reduce that if X is a linearly dependent set, then you can take a smaller subset, X prime, which spans the same vector space L. Indeed, if the set X is linearly dependent, then some of its elements, say X sub n, can be expressed in terms of other elements, all but X sub n. Then this means that you can denote X prime by X prime the set of all other elements, and then in terms of X prime you can express all the set X, including X sub n, and in terms of the set X you can express all the vector space L. Then you deduce that L can be expressed in terms of X prime. This leads to a very important definition. A subset of the vector space V is called a basis of V if the subset satisfies two properties. First, B spans all the vector space V, and second, B is linearly independent. You see from this corollary that each set which generates V in some state, V is a span of the set, can be reduced to some smaller space. You reduce and reduce and reduce, and after some number of steps you get a linearly independent set which is basis. This follows that each set which is a span, each vector space which is a span of a finite set has a finite basis. Examples. A more general example, and very important one, is the standard example of a basis of the standard vector space of n vectors. This is the set that is called a standard basis. It consists of the following list of vectors. These vectors consists of one unit and all other coordinates zeros. So if you have an n-dimensional space, then you get n such vectors. So this standard basis consists of n vectors. For example, in the one-dimensional space you get the standard basis consisting of one vector, the number 1 in a real line. For two-dimensional space, R2, that is for the coordinate plane, you get the two-element basis. The next more general example is about a system of linear equations. Consider a homogeneous system of linear equations associated to an n by m matrix A. Then the set of solutions L is a subspace of R sub n of Rn, and this subspace has a basis. Indeed, this basis we have considered under the name of a fundamental system of solutions. So the number of elements of this basis is n minus rank of A. This vector space L has a notation n of A. This is the null space of the matrix A. Now let us point an important property of basis of vector spaces. Proposition: all bases of any vector space has the same number of elements. So, given a vector space, we have a number associated to it. This number is called the dimension of V. It is denoted by dV. Note that, for example, the dimension of one line is 1. The dimension of the plane is 2. The dimension of our space where we live all is 3, because it's a three-dimensional space. We have 3 coordinate axes, and moreover, the dimension is equal to the minimal number of elements that spans V. Indeed, the number of elements of the basis is equal to the dimension. So, if you have a basis, you can't subtract some elements from the set to generate the same vector space. So, this is indeed the minimal elements. Or, an equivalent definition is that the dimension is the maximal elements which are linearly independent in V. For example, in a plane, you can imagine 2 linearly independent vectors, but you can't construct 3 linearly independent vectors on a plane. That is why plane is 2-dimensional. Look at the examples. First examples, as we discussed before, is that the coordinate plane is 2-dimensional, as well as any plane, and generally the n space is n-dimensional, because, as we discussed before, its basis contains n vectors. The next example might be the zeroth one, because there exists unique null-dimensional subspace or zero-dimensional subspace. It consists, or zero-dimensional space, which is a subspace of any vector space. It consists of the single null vector. The next example is a little bit less obvious. To any m by n matrix A, one can associate several vector spaces. First of them is the span of the columns of the matrix. It's called range of n, of A. And the second one is the span of all rows of the matrix. It is the same as the span of the columns of the transpose matrix. So that both these vector spaces have the same dimension, which is equal to the rank of A. And in a sense, complement vector space is the null space of A. We have mentioned that it contains n minus rank A linearly independent vectors, the fundamental system of linear equations, so that its dimension is equal to this number. The same is true about the null space of the transpose matrix. Examples. Of basis. Firstly, the simple example is just a real line. Take any non-zero number. We can consider it as a vector in this vector space. Then this single vector form a basis. B basis is equal to the set consisting of single element A. Indeed, single non-zero element is linearly independent. On the other side, on the other hand, any vector x from this vector space, that is any number from this vector space, any real number, is equal to x divided by a multiplied by a. We can see that this equations is a linear combination of the basis vector a, which is equal to the vector x, so that this vector a can express any vector from this vector space as a linear combination of it. So it's a basis. Second, plane. Say R2 or any other plane. This is the origin. I claim that any two vectors which are non-collinear, that is, which are not on the same line, form a basis. Basis B consists of two vectors u and v, where these vectors are not parallel to each other, or u is not parallel to v, that is, uv not on the same line. L means line. Indeed, consider any vector x. Let me construct a parallelogram by providing one line parallel to v and second line parallel to u. Then you get this side of the parallelogram is some alpha multiplied by u. This is x. And this side of the parallelogram is parallel to v, so that it is some beta multiplied by v. So we can express x as a linear combination. X is equal to alpha u plus beta v. On the other hand, because these vectors are not on the same line, then they are linearly independent, so they form a basis of the plane. Now, our third example is the vector space Rn with standard operations of addition and scaling, so that I claim that any n linearly independent vectors, linearly independent v1, vn from Rn form a basis. This means just that we can express any vector x as a linear combination of them. That is x1 v1 plus vn multiplied by xn, say. We can rewrite this as follows, that if we get a matrix consisting of these vectors a, v1 is the first column, etc., up to the last column, a multiplied by x1 xn is equal to the vector x. If these vectors are linearly independent, that is, the matrix A has the full rank n, then this system of solutions always has a solution. The system of equations always has a solution. Then the solution is the list of coordinates of the vector x on the basis v. It is indeed a basis. And the last example, as we considered before, recall a homogeneous system of linear equations. Here A is of any size m by n. This is a zero vector on the right hand side. And the set of solutions of this homogeneous system is a vector space as we said before, then it has a basis, and indeed a basis of S is just a fundamental system of solutions. A fundamental system of solutions. Fundamental system of solutions, by definition, it's a set of linearly independent solutions such that any other solution can be expressed in terms of them. This is a definition of the basis of S on other terms. So these are the examples of basis.
Now we will continue with the notion of a rank of a matrix. First of all, I will recall what is linear dependence and independence. So the columns of our matrix are called linearly dependent if there exists some, for example, real numbers alpha 1, alpha k, such that linear combinations of these columns a1, ak with these numbers, which not all of them equals to 0, this linear combination is 0, equals 0. So in this case, these columns are called linearly dependent. If linear combination equal 0, if and only if all coefficients, all numbers alpha I equals 0, these matrix columns a1, ak are called linearly independent. So the rank of a matrix is just a maximum number of linearly independent rows. So it's a natural number that is corresponding to a matrix. We could calculate the rank by applying a Gaussian elimination process to a matrix. Here you can see a very simple example. If we consider matrix A on the left and apply Gaussian elimination process to obtain row echelon form on the right side, we can easily see that we have two independent vectors here, and this means that the rank of the matrix A is equal to 2. Here you can see a very simple example of calculation of a rank in NumPy. Theorem about matrix rank states that the rank corresponding to rows of matrix and the rank corresponding to the columns of matrix are the same. So the maximum number of linearly independent columns equals to the maximum number of linearly independent rows. In this video, we will discuss the set of solutions of a system of linear algebraic equations. So our first statement is a theorem about the homogeneous system of linear algebraic equation. This means that we consider this system of type A, this matrix, multiplied by vector x equals vector 0. So for any such system, the set of solutions is a vector subspace in vector or linear space Rn, and the dimension of such subspace is equal to n minus rank of our matrix A. So the idea behind this theorem is very simple. We should prove that the set of solutions forms a subspace. This means that if we add two vectors or multiply a vector by a number, or more generally consider a linear combination of two vectors from the solution set, then this linear combination also belongs to the set of all solutions. And the proof of this fact is very easy. We just consider this kind of linear combination and apply our matrix to this linear combination, and we obtain, here you can see this, we obtain that the result equals 0. This means that our linear combination is a solution. The dimension of this subspace is n minus rank of matrix A, because if we apply Gaussian elimination process to our matrix, then the number of basic variables equals to the rank of matrix. So the number of free variables equals to n, the number of all variables, minus rank. And this means that we have n minus rank parameters that form the dimension of our subspace. So we could write down a formula for solutions of a homogeneous system of linear equations. We could obtain the decomposition of arbitrary vector x as a linear combination of the basis of the subspace that we discussed before. For convenience, I introduce the number k equals n minus rank of A, and the formula for solution is quite simple. X equals the linear combination of x1, xk, and this linearly independent solution, the basis of solution set, is called fundamental system of solutions. So we could decompose an arbitrary vector x. For example, this vector x you could receive from your friend via your favorite messenger. And if you have this fundamental system of solutions, x1 and xk, you could find numbers alpha 1, alpha 2, alpha k, such that these numbers help us to represent the solution x that we obtained from our friend as a linear combination of our fundamental system of solutions. We could obtain such decomposition by applying the Gaussian elimination process to the initial matrix A. And in this slide, we discuss the relationship of solution set of homogeneous system with a matrix A and in homogeneous or general system AX equals B with the same matrix A. If we have x0 as a solution of AX equals B and x1 is a different solution of the same system, then the difference is a solution of corresponding homogeneous system. The proof is again very simple. We consider the difference x1 minus x0 or vice versa, x0 minus x1, and apply our matrix A, and we obtain that it equals B minus B, so this is a zero vector. So this theorem about an arbitrary solution of a general system of linear algebraic equation tells us that an arbitrary solution, this means that this solution we could obtain from somewhere else, from our friend or from our favorite newspaper, for example, and we always can present it as a sum of some partial solution x0 plus the general solution of homogeneous system, and the final formula for the solution is x0 plus the linear combination of x1 xk and x1 xk are all belong to the fundamental system of solution. Here k is equals n minus rank of A. The proof of this theorem is very simple. We simply consider the difference of given solution x and our partial solution x0, and this difference should be the solution of the homogeneous system, corresponding homogeneous system, and we could apply our previous theorem. We know that all solutions of homogeneous system could be represented as a linear combination of fundamental system of solutions. Let us consider an example of finding the solution set of a general system of linear algebraic equation. So, example here consists of four equations, four linear algebraic equations with four variables. By applying the Gaussian elimination process, we obtain the reduced row echelon form, and for our given matrix A, it looks like this. So this row corresponds to the first equation, and the second one is like this. So, and we have also two zero strings in our reduced row echelon form, but I will not write them down because the equation 0 equals 0, this equation doesn't add any information to our solution set of solutions. So we will deal with this kind of reduced row echelon form. And reduced row echelon form means that the leading coefficients are ones, and all other entries in the columns where leading entries are equal to 0. So these equations could be written down as the expression of leading variables through the free variables. Namely, we could write them down as such two equations. And we could express x1 and x2 via x3 and x4. Namely, we could write it like this. So it's and this means that if we consider an arbitrary vector x, it belongs to the solution set if and only if these two variables x1 and x2 are expressed like this via x3 and x4. So this means that we could, instead of x1 and x2, we could write down these two expressions. So here and here, and it will be like this. So it's a general solution of our initial system of linear equation. And we could decompose it like the sum of the partial solution of initial and homogeneous system of linear algebraic equation and the general solution of a homogeneous system. Let's do it. And this is the partial solution of our homogeneous system. So in our theorem it's x0, and this is the general solution of a homogeneous system. And this general solution or representation of solution sets looks like a linear combination of two vectors, namely E1 and E2 and these two vectors forms the basis of our set of solutions, and this basis sometimes called the fundamental system of solution. So these two vectors, E1 and E2, is a fundamental system of solution for our homogeneous system of linear algebraic equations. To sum up, we have this form of solution for our initial system of linear equations. And this means that we have some linear subspace here, and it is shifted by this vector. So in some sense, the solution, the set of solutions of system of linear algebraic equations is always some subspace shifted with some vector of partial solution. Now we will discuss a Rouchet-Capelli theorem. And this theorem is just a criterion for existence of solution. So if we consider the system AX equals B, it has solutions if and only if two ranks are equal: rank of matrix A and rank of matrix A B. Matrix AB is a matrix where we add one column, namely column B, and this is a matrix with the same number of rows, and the number of columns is n plus 1. To prove this theorem, we could simply write down our system in the vector form. This means that we could write it down as the linear combination of columns A1, An with unknown variables x1, xn, and this linear combination equals B. So the system has a solution if and only if vector B could be expressed as a linear combination of the columns of our matrix. So this means that the maximal number of linearly independent columns in A and in A plus B are the same if and only if the system has a solution. So as the maximal number of linearly independent columns is, by our definition, is rank, so this means that two ranks coincide if and only if our system has at least one solution. Let us consider a simple example of such situation. We have a matrix A here, and its rank equals 3. We could see it by applying Gaussian elimination process. Consider a reduced row echelon form here. And if we consider the matrix A plus B, I mean not an addition of two matrices A and B, but just a concatenation of A and B, like on this slide here. And the rank of this matrix is 4. So this means that by our theorem, this system of linear equation is inconsistent. It doesn't have any solution. This vector B couldn't be expressed as a linear combination of columns of our matrix. So the number of linearly independent vectors in this case, in matrix A, B, is greater than 3. Now we will discuss rank decomposition, or sometimes it is called full rank decomposition. And the statement, the precise statement, looks like this. If we consider an arbitrary matrix A and its rank equals R, so R could be not bigger than the number of rows m and number of columns n, there exist two matrices B with m rows and r columns, and matrix C with r rows and l columns, such that our matrix A equals the product of these two matrices B and C. So this means that we are finding the decomposition of A as a product of B and C. So it's just an example. Maybe you do remember it from the first video of this week. So this matrix of size 4 by 4, could be expressed as a product of two matrices. So the matrix B has 4 rows and only 1 column, because the rank of this matrix A, given matrix A, is equal to 1. And the second matrix C is just 1 row, 1 string, and it's also because of the situation where rank of given matrix A equals 1. But how to find the rank decomposition in an arbitrary case? There are several ways to find it, and one of these ways is just a byproduct of Gaussian elimination process applied to our matrix A. For a given matrix A, we could obtain a reduced row echelon form by applying the Gaussian algorithm, and then we could take the matrix C from our statement about full rank decomposition as a matrix of reduced row echelon form without 0 rows. So this would be the matrix with exactly R rows, where R equals a rank of matrix A. As matrix B, in this case, we could take the columns of matrix A corresponding to the leading coefficients in reduced row echelon form. So it also has exactly R columns. So these two matrices are of needed size. And what is the reason for their product be equal to initial matrix A? The reason is that we select the basis of the span of the columns of the given matrix, and the matrix B gives us this basis. So the matrix C gives us the coefficients with which we should take our columns to represent an initial matrix A. This is true just because of the definition of matrix multiplication. Let us consider a very simple example of such thing. For a given matrix A, we have 3 rows and 4 columns. We obtain a reduced row echelon form on the right-hand side. And the rank of this matrix is 2. So to obtain matrix C, we just eliminate 1, 0 row from the reduced row echelon form. So the C is just the matrix of reduced row echelon form without zero string. And for matrix B, we take the first 2 columns of our matrix. So matrix C here presents that we should take the coefficient 1 to obtain the first column of matrix A, the coefficient 1 to obtain the second column of our matrix A, coefficients 1 and -1 to obtain the third column, and coefficients -1 and 5 to obtain the fourth column of our matrix A from the columns of matrix B. Now we will discuss the application of rank decomposition to compression of a scanned document. As an example of scanned document, we consider this rectangular black and white matrix with the poem by Longfellow. So each entry of this matrix has one of 2 values. For example, 0 or 1, this means black or white, this pixel is. So we could apply our rank decomposition to compress this image, namely to obtain 2 matrices that will have smaller size. We could note that it could reduce the size because in this matrix we have many totally wide or rows or totally wide columns. So this compression could be useful. We should note that it's not the best way to compress an image or even scanned document. And we should note that linear algebra has some more efficient tools, but we will not discuss it now.
To model some abstract vectors as n vectors, you should introduce some kind of coordinates in an abstract vector space. Suppose we have an n-dimensional vector space V, so that we have a basis B consisting of n elements. Then, for each vector x from this vector space, there exist some numbers which gives a linear combination of the basis which is equal to x. Indeed, the basis should span all vector space, so that each vector from this vector space is expressed in terms of the basis. The numbers which appears in these linear combinations are called coordinates of the vector x in the basis B. So that the coordinates depend not only on the vector x, but also on the basis B. Given a basis, we can denote the column of four coordinates by x sub b. For example, if you remind the standard basis of the vector space Rn, then the standard column vectors are just coordinate vectors of each element of R sub n in this standard basis. So that for Rn, the coordinates are the same as the coordinates in the standard basis. In general, you can express an abstract vector x as the following matrix product. Look, the first row of this product is just the list of symbols of abstract vectors b1, bn. And the second terms of this product is the column of numbers, so that after multiplication you get this linear combination x1 multiplied by b1, etc. This is in a compact form, just a matrix product, so that you can express this in this form. Lemma. Given a basis and a vector, the column of coordinates is unique. This means that all these coordinates are uniquely defined by the vector and the basis. x1 and x2 and xn, all of them are defined uniquely. So the whole column of the coordinate is corresponds to the vector x. Let us prove this very important lemma. Suppose there is another coordinate column of the same vector x. We should prove that this another coordinate column is equal to the original one. So we have two expressions of the vector x as linear combination of the same basis b, but with different coefficients. Subtract from the last row the right hand side, you get the following equality. By rearranging the summands, you get the following simple form of the same equality. But look, this simple form is a linear combination, which is equal to null vector. But this is a linear combination of the basis b, so that a linear combination of a linearly independent set of vectors. By the definition of that linear independence, we can deduce that all coefficients of this linear combination are zero, because this linear combination should be trivial. This means that all the coefficients are zero, or x1 is equal to x1 prime, etc. up to xn, which is equal to xn prime. This means that the two columns of coordinates are the same column. So the coordinates are unique. Now, in a more abstract language, we can say that we get a function which for each vector x calculates its coordinate column. This is a map or function or operation which can express each abstract vector as an n vector. Moreover, reversely, given an n vector and a basis b, you can calculate a vector with these coordinates. So each column vector you can imagine as a coordinate vector, and for each abstract vector you can calculate the column vector or coordinates. So you have a correspondence between two sets. One is an abstract n-dimensional space, and the second one is the set of columns of coordinates, that is, the vector space of n vectors. So abstract vectors are in one-to-one correspondence with n vectors. This is a very important point because it allows us to model each n-dimensional abstract vector space as an n-space, and n-space is a universal model for each n-dimensional vector space. To formalize this, let us list the properties of this map from an abstract n-dimensional vector space to the space of n vectors. The first two properties are called linearity. First, that if you scale the vector x, then you scale the coordinate column. If you add two vectors to each other, then it is the same as to add two coordinate columns to each other. It follows that if you have several linearly dependent vectors or linearly independent vectors, then their coordinate columns are also linearly dependent or linearly independent. And it follows that if you have a basis, then the coordinate columns of these vectors form a basis of the space of n vectors, and so on. If one vector is equal to a linear combinations of other ones, then the coordinate column of this vector is equal to the linear combination with the same coefficients of the coordinate columns of that vector, and so on. These properties of the map phi are very useful in many situations. Such maps are called isomorphisms. So, in a most abstract language, we can say that each abstract n-dimensional vector space is isomorphic to the space of n vectors. Or, from the mathematical modeling viewpoint, we can say that the set Rn is a universal model for all n-dimensional vector spaces. Now, let us consider the following situation. The basis is not unique, so we can imagine two bases on the same vector space, B and B prime. This means that all elements of the second basis can be expressed in terms of the elements of the first basis. That is, each element bj prime has a coordinate column. We denote this column by tj. This is just a column vector of n numbers, and you can arrange all these columns to organize an n by n matrix, which is called a basis transformation matrix. This matrix contains the all needed information to express one basis in terms of another one. Not every matrix can be a basis transformation matrix for some basis. For example, if T is a basis transformation matrix from B to B prime, then it should be non-degenerate. The first example of a basic transformation matrix for each vector space is just the identity matrix. This is a transformation from a basis B to the basis B. This means that the columns of the identity matrix express the elements of the basis B in terms of themselves. So, in the coordinates associated to the basis B, the elements of the basis B look like the standard basis elements of the vector space Rn. The second property, that if you have three bases on the same vector space and you have a transformation from the first basis to the second one and from the second to the third one, then the total transformation from the first to the third basis is the product of two matrices. One can deduce from the first two properties that the transformation from one basis to another one, give an matrix inverse of the matrix of the transformation from the second basis to the first one. So the inverse transformations give the inverse matrix. In particular, of course, as I said before, the basis transformation matrix should be non-degenerate. Now, if you have two bases, then each vector has two coordinate columns, x sub b and x sub b prime. All information about the connection of two bases is in the basis transformation matrix T. So, in terms of this T, one can calculate the new coordinate in the terms of the old one or vice versa. The simple formula is to calculate the old coordinate in the terms of new one. Look at the first formula. And to calculate the new coordinate, the most natural problem, you can use the matrix inverse, or, as the same, the matrix of the inverse transformation. These are many very important formulas which will be used not only in the algebra problems, but also in analysis problems. For example, consider a coordinate change on a plane. Let it be the coordinate plane R2 with coordinates x and y. As usually, this is the origin 1, 2, 3, 4, 1, 2, 3, minus 1, 1, minus 1, 1, minus 1, minus 2, 2, 2, 3, 4, minus 2. Okay, let us introduce some non-standard bases on this plane. The basis A, let it consists of two vectors A1, say 1, 1, A2, say 1, minus 1. And let the basis B consists of the vectors B1 and B2, which are B1 is 2, 1, and B2 is minus 1, minus 1. So, this is the vector A1, this is A2, and that are 2, 1 is B1, and also B2 minus 1, minus 1. Where is it? Here. Okay, there are two bases, and suppose we know coordinates of some vector x on some basis. For example, we know that the vector x written using the basis A has the coordinate column, say 2, minus 1. If you add 2 this and minus 1 that, then you get a vector x. We'll calculate what is it. Okay, and also we have the standard basis E, E1, E2. The basis E is always a standard basis of the Rn, in particular on the R2. E consisting of these standard basis vectors. Okay, let us find x where the basis B, the coordinates of x on the basis B, and let us find x itself. X itself is the same as x the coordinate column of x on the basis E. Okay. To do this, let us calculate the change of coordinates. That is, we have the matrix of coordinate change from E to A is the matrix consisting of the vectors of the basis, that is the vectors A1 and N2 written via the basis E. That is just standard coordinates of these vectors. Analogously, the coordinate change matrix to the basis B, sorry, not A, B, is equal to the list of columns of the vectors B1 and B2, that is 2, 1 and minus 1, minus 1. How to calculate the coordinate change between the two bases A and B? Firstly, let us note that which the direction of the coordinate change we need. We need to calculate xb, and we know xa, so that we need the matrix T from B to A, where the matrix can be calculated using these two known matrices. That is T from B to A, E, and then from E to A, or the known matrix 2 power minus 1 multiplied by T from E to A. This is what we need, and now let us calculate what is it. Here one can calculate the matrix inverse of this guy, and you get the matrix, I know the answer, 1, 1, minus 1, minus 2. Well, then we can calculate, so the matrix we need is this guy, multiplied by that guy, that is what is it, column, row by column 0, here 1 plus 1, 2, here minus 1, and here this row by that column 1 plus 2, 3. This is a matrix. We have then x on the basis B is equal to this matrix multiplied by xa. xa is the given vector. So we have the vector minus 2 and minus 5. So these are the coordinates of x on the basis B. And also, what is x itself? It is easy. More easy because x on the basis E is just T from E to A multiplied by xa. That is this matrix multiplied by the same vector xa, and you easily get this matrix 1 1 multiplied by that vector 1 3. Is this okay? 2 minus 1 1 and 2 plus 1 3. Okay, let us return to the picture and place the vector x. 1, 3. This is the vector x. And indeed, x should be 2 multiplied by a1. 2 multiplied by a1 is this vector, plus minus 1 multiplied by a2. Minus 1 is this vector, minus a2. Okay, indeed, this is x, and what does mean that the coordinates on the basis b are minus 2, minus 5. Then, if you multiply b1 by minus 2, you go somewhere towards the left, and then plus minus 5 multiplied by b2, that is, you get some plus minus 5 b2, then you go to the same point, the end of the vector x. Euclidean space. We have described abstract vector spaces and compared them with Rn, the space of n vectors. So now we know that the standard linear operations, addition and scalar multiplication, allows us to rearrange some data to make one vector from another vector and one matrix from another vector matrix, etc. But in many practical problems, we would like to associate to the column of data or a matrix of data some number, some estimate. For example, the price, or for example, the efficiency, or some other number, because we would like to estimate something. Just to calculate the norm of the vector or the length of the vector, it is very important in geometrical problem. So, how to measure vectors in a vector space? To do this, we should introduce some other operations. And to introduce this, we give a new notion of Euclidean space. What is it? Some people say that the Euclidean space is a space where Euclid lived. And moreover, Euclid has described the space where he lived, and he gave several geometrical axioms and theorems which gives a way to calculate angles and distances and, for example, squares, etc. Volumes maybe. How to do some estimates, some measures in abstract vector spaces. We need some additional operations, like distances and angles and measures, but in fact we need only one additional operation. Definition. Suppose epsilon is a vector space. We call it epsilon because this is the first letter of the Euclid name. A function which associates a number to a pair of vectors is called a dot product, or maybe scalar product, but it is not good because of the multiplication by scalar, or inner product, if it looks like standard dot product. That is, it satisfies the property of symmetry, the property of bilinearity, that is, if you multiply a scalar product by a number alpha, then you can, with the same result, multiply only one element of the product by the alpha. Or if you sum two products, then you can rearrange them if you have a common multiplier. Bilinearity, look at this formula. This is standard. And the third one is non-degenerity, sometimes called, but the most common name is positivity. It is positive if you multiply a vector by itself, and the vector is not a null vector. So this space epsilon is called a Euclidean space. So the Euclidean space is an abstract vector space with two operations of addition and multiplication by a scalar and one additional operation on it. Dot product. Generally, you can define several Euclidean spaces with the same underlying linear space. Not that. So this means that you can define different scalar products for the same abstract vector space. But in standard examples like Rn, you define the most natural scalar product, and then using this natural scalar product you can measure each vector, a length on a vector in a Euclidean space is just the square root of that positive number, its square in terms of dot product, a dot product of the vector by itself, and square root of it is called a length. For non-zero vector is a positive number, for zero vector is 0, so this length can distinguish zero vector and non-zero vectors, and also this length do satisfy the standard properties. If you scale the vector by number alpha, then the length is scaled by the modulus of alpha. Look at the property number 2. You multiply the modulus of alpha in the right side by the length of the vector x, and then you get the length of the vector alpha by x. And the third property is called the triangle inequality. This is the only connection of the length and the addition of these two operations. If you calculate the sum of two vectors, then it has a length which is maybe less or, in the best case, equal to the sum of the lengths. This is the property of a standard Euclidean triangle. If you imagine a plane, a standard plane with standard geometrical vectors and geometrical points and lines and, for example, circles, then all Euclidean axioms are satisfied by the vectors on this plane. The standard Euclidean axioms and postulates that was created by Euclid about 2000 years ago, and also the properties of this dot product also hold by the vectors on it. So each plane is a Euclidean plane. And as well as on a standard Euclidean plane described by Euclid, you can describe an angle between two vectors in terms of the dot product. The cosine of two vectors is calculated by this formula. If the vectors, if at least one of these vectors is 0, then the cosine is undefined. But if the vectors are non-zero, you can calculate the angle. For example, the angle is equal to pi by 2, that is, the vectors are perpendicular to each other, or the same is to say that they are orthogonal to each other, if and only if the scalar product is equal to 0. In this definition, the zero vector is assumed to be orthogonal to each other vector. That is, to find two orthogonal vectors, you don't need to calculate their length, but just the scalar product. That is, inner product. It is denoted by this sign of orthogonality. If you have angles and distances in a Euclidean space, then we have all theorems of elementary geometry that was created by Euclid and all ancient mathematicians. For example, we have triangles, we have some standard properties of triangles, and in particular the most famous theorem, that is Pythagoras' theorem. If you have a triangle, that is three vectors x, y, and x plus y, such that x and y are orthogonal to each other, then you have the Pythagoras theorem that the square of the x plus y is equal to the sum of the squares of x and y. Let us look at examples. Euclidean space is an abstract vector space, first of all, so that there are some bases in this space. In an abstract vector space, all bases are more or less equivalent, but in the Euclidean space, where we have distances and angles, we can separate and find some good bases, among others. First, a basis E of a Euclidean space epsilon is called orthogonal if all its elements are orthogonal to each other. That is, the scalar product of each two elements of the basis is zero. So this property is easily described in terms of scalar product. So good basis is an orthogonal basis in a Euclidean space, but a very good basis is an orthonormal basis. This basis is more or less equivalent to the standard basis in the vector space Rn. That is, this is orthonormal basis, which is orthogonal and normal. That is, all its elements are orthogonal to each other, and moreover, all its elements are normal. That is, they have unit length. So, an orthonormal basis in a plane is, for example, the standard basis consisting of two unit vectors. But there are also some other orthonormal bases on the same plane. Generally, an orthonormal basis in a Euclidean space make us a possibility to consider the space as an analogy of the vector space Rn. That is, consider the coordinates on an orthogonal basis. So, in these coordinates, the scalar product can be calculated by the same formula as a standard scalar product in the n space. That is the sum of the product of corresponding coordinates of the vectors, or in the language of the matrix multiplication, you see the formula x transpose multiplied by y, where x and y are represented as columns of coordinates in an orthonormal basis. So in each orthonormal basis, the scalar product is calculated by the same formula. And moreover, because the length of a vector is calculated in terms of the scalar product, so for the length of vector represented in an orthonormal basis, we have the same formula. Recall that an angle between vectors and some other measurements are represented in terms of scalar product as well, so that the dot product of two vectors give us the same formula for the length of a vector as in the standard vector space Rn. That is why, if we choose an orthonormal basis in an abstract Euclidean space epsilon, then you can consider this vector space as Rn. Or, if you want, you can consider Rn as a model for this vector space, and all vectors are then represented by the coordinate columns, and all lengths and angles and so on you can calculate by this in the standard way. distance in Euclidean space? In Euclidean space, we can identify its elements, vectors, with its ends, so that we can consider the vectors as points of a Euclidean space. Then the length of a vector is the distance between the 0 and the end of this vector. What is the distance between two elements of the Euclidean space? You see, it's just the length of a vector beginning from the one point and ending on the other point. That is the length of the vector b minus r for two vectors a and b. But what is the distance between some, say, point and a plane? Or maybe some other subspaces on a Euclidean space? You see that usually we are interested also on this distance, for example, between, say, Moon and Earth, or some other physical objects. Obviously, we can give a standard definition. The distance between two subsets x and y of the Euclidean space if the minimal of the distances between points of the one subset and the other subset. Of course, this work only if such a minimum exists. If it doesn't exist, you can replace minimum by infimum or so on. But it doesn't matter for us now, because we are mostly interested in the distances between some linear things such as planes, hyperplanes, lines, points, and so on. But how to calculate this distance, at least for these linear things? To calculate it, you need one additional concept, which is the orthogonal projection. Suppose L is a subspace of our Euclidean space epsilon, and let x be a point or the vector on another language. Then you can represent x as a sum of two vectors. One of them is a vector from L. It is called an orthogonal projection. And H is orthogonal to any vector from L. That is, H is orthogonal to L, simply to say. So we can prove that these vectors exist and unique, so that they have their own names, and the pi is called the orthogonal projection, and H some is called like an orthogonal component of x with respect to, and so on. And pi is the orthogonal projection of x onto L. Look at this picture. Here the horizontal line is L, and the vector x is represented as a sum of two orthogonal vectors. One of them is pi. This is you see, this is a vector from L, and H is orthogonal to L. So the sum is x, and we can, if you see the L as a horizontal plane, then pi is horizontal, H is vertical. Proposition: the distance between the vector x and the space L is equal to the length of H, so that the length of this vertical component. That is, you can calculate it using the projection pi by x minus pi. This is the vector which length is equal to the distance. Or, on another language, the shortest path between the point x and the subspace L is via H. How to calculate the orthogonal projection? And then using this one can calculate H, and so that you can calculate distance using it. So suppose the vector space L is described in terms of its basis, so that you have m vectors of epsilon. These vectors are linearly independent, and suppose that these m vectors form a basis of L, so that L is m-dimensional. Now we have the following formula for the projection. Look, it is one of the longest formula in our course. It's a product of four matrices: A transpose, A transpose, and there is a matrix inverse inside it, so that you can look only the word AT if you omit the parenthesis and -1, maybe ATX. This can help you to recall this formula. We will not prove this proposition, but let us formulate the corollary. This corollary should be clear after the previous consideration. If you know the projection, then you can calculate the orthogonal component, which is equal by its length to the distance between x and the vector space L. This distance is equal to, you see, x minus this projection, or you can rearrange it by a matrix multiplied by x. The matrix is equal to I minus that AT. Now let us discuss some applications of abstract algebra of linear spaces, including Euclidean spaces. First of these applications is the least square solutions. We will discuss how to solve inconsistent systems, that is, how to solve the systems of linear equations which has no solutions. The second application is linear regression. It is the most popular method of making prognosis of some temporary data. And the third application is the support vector machine. That is one kind of linear classifiers which can classify some objects into two classes, which is this is useful in machine learning in many applications. First, least square method. Consider an inconsistent system of linear equations. That is, a system of linear equations in n variables x1, xn with m equations which has no solutions. That is, we can solve it exactly, but we can think about an approximation of the solution. Let this approximation is a vector x hat. What is an approximation? How to find the vector which is most close to the possible solution? It is not clear maybe even how to formulate this mathematical problem. Let us consider the following classical approach. Given x, an element of Rn, let us calculate the square of the distance between the left-hand side and the right-hand side of this system. That is, the length of the vector ax minus b squared. Because we don't like square roots, so let us calculate the square of the length of the vector rather than the length itself. This value d of x should be minimized in order to find the most close approximation for the solution. So we can't solve this exactly, but we can find x which more or less solves this system. So our aim is to minimize d of x. Let us consider the geometric interpretation of it. So let L be the subspace of R generated by the columns of the matrix A. So remind that there is a small number of columns n generally, but for inconsistent systems generally there are a lot of equations but small number of variables. So these are very high columns and there is a small amount of them. So we have such a rectangular matrix A, and now d of x is the distance between b and ax squared. So if you want to minimize d of x, then you want to find such x that the distance of b and ax is equal to the distance of b of L, because this d of x can be less than the distance of b and L squared. So the minimal value is for such x that this equality holds. Now recall that this happens if ax is equal to the projection of the vector b onto L. Then d of x is equal to the length of the orthogonal component squared. How to find this x? Proposition. This x, which is the least square solution, for the matrix A of full rank is unique and is calculated by this formula. It is a common situation when this matrix is of full rank, but for some rare situation where it is not a full rank, there are generalization of this formula based on the pseudo-inverse concept, but don't matter. So look at this formula. This is more or less close to that formula of the projection. And now if you have this formula for x, then you can calculate d of x, and so this is the square distance, which is the equal to which is equal to the square of the orthogonal component of the vector b onto L. Proof. Let A small be the set of columns of A. Note that it forms a basis of the vector space L, because this set generate L, and all these columns are linearly independent because A is of full rank. Then d of x is minimal if and only if ax is equal to the projection of B onto L, because it is minimal for the case then the difference between the left and the right hand side is equal to the orthogonal component squared, as we said before. So let us note that in this situation, if we assume that ax is equal to the projection, then x hat is unique, because x hat is the vector such that if you multiply the first column by x hat 1 and plus the last column multiplied by x hat last coordinate, then it should be equal to this projection. So x hat represents the column of coordinates in the basis A of the projection. So because the coordinates are unique, then x hat is unique if it exists. Why it exists? Because if you choose x hat calculated by that formula that we have seen in the formulation of the proposition, then look, ax is that at b, that is, this is a projection of the vectors of the vector b on L. So for x calculated by this formula, we get ax is equal to projection. So for this x, d of x is minimal, and because it is unique, we deduce that x hat is equal to this thing. So we see that x hat is the projection, and the distance squared, that is the least squares sum, is equal to the length of the orthogonal component of the vector b with respect to L. Now, linear regression. This is the next application of those tools of the Euclidean spaces, and moreover it is an application of the least square method. Let us, for example, of application of the least square method, consider an unknown linear function. Suppose that some process on some, for example, set of data is described by a linear function on m variables, x1, xm. So it is linear with some unknown coefficients, c1, cm. To evaluate the coefficients, we can organize some experiments. In these experiments, we can measure both the vector x and the value y. Of course, we should accept that there might be possible errors in these coefficients. So maybe these values of x don't belong to this plane represented, or hyperplane, or the line represented by this formula. So we would like to minimize the error. Look at this picture, which represents the case of one dimension. So the unknown y, or the function y, is a function on one variable x, which is equal to x1, and then we have some points. Ideally, these points lie on the same line, but because of the errors of the experiments, these points are close to some line, but not exactly on the line. So look at the picture. There might be some optimal line or some non-optimal line. In this picture, we see that the non-optimal line is far from the points we pick, and the optimal line is the closest in a sense. In what sense? We would like to minimize the error of the equalities. For each experiment, the the equality should be of this form: y of x should be equal to what we calculate on the in the right hand side, or simply the scalar product of the ith x by the unknown vector c should be almost equal to the y sub I. Now let A be the matrix which rows are the x's from the experiments. So the ith row corresponds to the ith coefficient. This is a matrix of a linear equation AC equal to y, where A is the matrix of the system, C is the vector of the unknowns, and y is the right-hand-sided vector, the vector of right-hand sides. So, to solve the problem, we will find the least square solution of this system, C hat. By the previously known formula, we get that C hat is equal to this guy. For example, for m equal to 1, that is in the one-dimensional case, recall that graph. How to find the optimal line? By this formula. In the one-dimensional case, the matrix A is just one column, and then we can calculate C, one single number, by the formal formula. You see that this is a product of the row A, so of the vector A by the vector y divided by the squared length of A. So for normalized A, it is just a scalar product. This is the formula for the optimal line. The next application is one of classical linear classifier support vector machine. Let us look on the board. Consider an example of linear regression model applied to some toy situation. Suppose we want to find a line which is most close to 3 points. For example, for example, these points, 2, 1, this point, 2, 1, there would be such a line, but the third point not lie on that line, so that it lies outside it. This is the third point, with the coordinates 3, 3. How to find the line which is the most close to all 3 points? We would suppose that the line should be somewhere, for example, let it be a white one, because it just has a position, maybe somewhere on this direction, 4, 4, and something like this. But the exact parameters should be found using that linear regression model. Okay, we have that for 2 coordinates x and y, we have the following values for the coordinates x, y. These are our 3 points. X is equal to 1, y 2. Y is equal to 1 when x is equal to 2 and x is equal to 3 as well as y. So we want to find some line, that is, we want to find a line of the form y is equal to kx plus b, a standard form of a line, and we have an approximate system of linear equations. What do I mean by the approximate system? So that for this is I is equal to 1, 2, 3. For each y, for each I, index from 1 to 3, we should consider an approximate equation of that form, where I is 1 or 2 or 3. Let us write out the approximate equations for each of our 3 situations. That is, we get a system of linear equations of the following form: k multiplied by 1 plus b is equal to 2. The first line, y number 1 is equal to 2. The second line, k by 2 plus b is equal to 1. And the third line, analogously. So we get a standard linear regression model, and we have an approximate solution, approximate equations or approximate solutions for the following system. We may write out as A multiplied by the vector KB is equal to the vector Y, which is the least of all y's, 2, 1, 3, where A is the matrix of the coefficients of the systems: 1, 1, 2, 1, 3, 1. Okay, let us solve it. We have that the solution for the linear regression model is the least square solution of this system of equations. That is, KB is equal to C hat. That is, we remember this formula, A transpose A minus 1 multiplied by AT multiplied by 1 y. Let us calculate all the components. So AT is just 1, 2, 3, 1, 1, 1. A 1, 1, 2, 1, 3, 1 minus 1. AT is again 1, 2, 3, 1, 1, 1. 2, 1, 3. To continue the equation let us calculate separately this product and that product. We can rearrange the ordering of the multiplications, but not rearrange the terms, so that this product one can calculate, and I have calculated already. It is this symmetric matrix. This matrix is usually symmetric because of this definition, power minus 1. And if you multiply this matrix by this vector, you just get a small 2 by 2 vector. 1, 2, 3, 2 plus 2 plus 9, 13, and 6. If you calculate the inverse matrix, you get the determinant is 6. 14 multiplied by 3 minus 36 multiplied by the conjugate matrix, that is the minus 6 minus 6, 3, 13, multiplied by this vector. And you get, if you multiply all of this, you get just with the vector of this form. Oh, sorry. So, let us return to the model. We have now that we know k and b from this equality. K is equal to 1/2 and b is equal to 1. Y is 1/2 x plus 1. That is the real one crosses the yx at the point 0, 0, 1, and then it has a slope 1/2. So after 2 steps by x, it has 1 step by y. So the most approximate line, the most closest line is this one. This is the solution. One another application of linear algebra in data analysis and machine learning is the concept of linear classifier. Linear classifier classifies some points on a plane or on a vector space from mathematical points of view. But from the engineering point of view, there are some, for example, clients or some cases or some strings of data, and we should classify them into two kinds. And we have a sample which is marked, which is already classified. Linear classifier. Linear classifiers. Suppose, for example, on a plane or on a vector space Rn, you have points of two kinds. For example, blue points and red ones. Red ones are and then suppose you have one unknown point and you should decide, is it red or, if this is a point, you should decide, is it red or blue? Red or blue? How to decide? The idea is the following. Put a line on this plane or a hyperplane on this vector space, if this is a plane, that it would be a line which divides the sample into red and blue parts. And then if this point on the one side of the line, then it is red, and if it is on the blue side, then it is blue. But now this point is unknown. This is unknown. Before you have this line, and if you have, then you should put color it as blue. The problem is how to find such a line. Of course, there are a lot of them. Maybe this line is here, or maybe here. What is the best line? What is the best way? One of this approach is based on some norms of vectors, and this approach is probably the most famous linear classifier. This is more or less old, and it is called support vector machine. Support vector machine. What are the support vectors? These points are vectors on the vector space Rn, and the nearest points from the blue side and from the red side are the support vectors. In this picture, these are two support vectors, but it might be more. They are the closest to the dividing line or a hyperplane. Okay, let me formalize the problem and then to say how to find the best hyperplane if the sample is divisible. Okay, suppose we have red points are, say, x1, xk, are of kind 1. So these are blue points, sorry. And the red points are k plus 1 xm of kind 2. We should put a separate line. First, let us consider the case of the plane, that is R2. Then this dividing line has the form dividing line. It has, for example, w1 x1 plus w2 x2. It has the equation is equal to some b. Or you can write here that the vector w known multiplied by the vector x of unknowns is equal to b. This is the standard equation for a line. And then the blue points has the following property. If you put blue point x here, then, for example, you may assume that it is you get the equality greater than b. So it's a positive half plane for I from the blue interval, I less or equal to k. And on the red side, xa is less than b for I greater than k. So these are the mathematical sense of the dividing. Now, the idea of support vector machine is the following. first how to do the same thing for the vector space Rn. Then it would be a hyperplane. So now it is not R2 but Rn, and this is a hyperplane, or in the case n is equal to 2, it's just a plane. But it again has some the same equation. That is, the equation of it is the following. Wx is equal to some b. The w is unknown vector. It is a normal vector to the hyperplane, and b is some constant. We can divide this equation by some number so that b may be chosen to be equal to be as small as possible, but generally then we can also assume that by dividing this equation by a number, that the distance between this hyperplane, if you the minimal value of this left-hand side is b plus some number for the positive part, blue part, and b minus some number for the negative part. Then assume that the idea to find the hyperplane is the following. Support vector machine solves the following problem. Finds w and b such that w is a vector, b is a number, such that first for blue points we have it is greater or equal to b plus 1. Next, for the red points, wxi is less or equal to b minus 1. So this is for e1 to k, this is for e k plus 1 m, and still such a plane is not unique. To be unique, it must be the best of all planes, and the condition that it is the best is that the length of the vector w must be as small as possible. I don't give you an exact description of the algorithm, but we can use the SVM methods for in each system of mathematical functions for machine learning and data analysis, and we'll try to use it using Python in some example after a few minutes. But now let me say some words what happens in the case when the sample is not divisible. What do I mean? Suppose that the sample is not exactly divisible, but it is almost divisible. That is, for example, there is one bad red points in the center of the blue region, and maybe there are a few blue points among many red ones. So this hyperplane is more or less good, but this problem has no exact solution, because even this system of linear equations, inequations, has no solution, because there is no exact dividing hyperplane. What to do in this situation? First case is to use some people say kernels for the support vector machine, that is to give some get some non-linear coordinate change in order to separate them linearly. But it is sometimes it is okay, but for some problems it doesn't work. And really, in general support vector machine method, the solution this problem has in real system some kind of soft margins. Soft margins means that we get the minimal sum of some functions of the following kind. Minimal of some functions of the following case. Lambda multiplied by, for example, the length of vector w square plus some loss function for the cases when these inequalities doesn't hold. For some, I don't give you details, some say, how to say, loss function, or some additions, some summons, one for each broken inequality, and that is for each inequality which doesn't hold. For is wrong inequality. You can find details, for example, even in Wikipedia maybe, but better to find some books on machine learning. But people use this method even if they don't know what are the exact summons for each wrong inequality, but we'll try to use this method in some situation. This is for non-divisible sample, but if the sample is divisible, then the support vector machine finds the minimum value of w such that this hyperplane divides as good as possible. Let me just say how it looks. For example, let me put here 1, 2, 3 points. Blue ones, and for example blue are crosses, so blue points. Where will be the support support vector machine hyperplane? Hyperplane here is just a line, and this line will probably be here, so that the distances between the support vectors, the closest points, should be as maximal as possible, and the distances for blue vectors and for red vectors should be equal. This is geometrically what the support vector machine found. So this is the division of the hyperplane. And then if you have some blue point and the dividing hyperplane of this kind, so what can we do to find if the unknown point x is on the blue side or on the left side? Just to calculate wx and compare this with b. If it is greater than b, then this is blue, and if it is less than b, then this is red. Okay, this is an intuitive description of the support vector machine, so that let us try to use it. Now let us discuss how to calculate both linear regression and SVM using standard Python functions. Using them, we can calculate both linear regression and SVM and many other things in a very simple way, just in one or two string of the code. Let us begin with linear regression. First, we use a Skylearn package, and you see we import linear regression functions from them. First of all, we prepare the data. You see X is an array of 20 more or less random numbers from -7 to 7. And let us calculate Y as triple X plus 7 linear functions plus some random noise. Random noise, you see, it is uniformly distributed for each X. So now we see we train the regression. That is, we use all the data X and Y to calculate the linear regression module. And then we calculate Y hat. You see, this is a prediction of our models for all X's. And now we can construct a graph of what we have. You see the methods of construction of the graphs. Later we'll say where to find the exact code to construct all of this. And now you see that the red line is the linear regression model, a line from that model, and the blue points are our data. Indeed, our line is very close to all our points, and you see that it nicely approximates all these points, and so we can predict the next y's for next values of x up to that random noise. Now let us consider an example of using SVM via Python. Again, we use the Skylearn package, and here we prepare the data for using SVM with the function makeBlobs. It creates two clouds of data around two different centers. So we can hope that the SVM classifier, simply SVC, support vector classification, support vector classifier, will distinguish one cloud from another one. Now we see that we use the SVC function. The words kernel is linear means that we use the classical SVM with no additional kernels, that is, no additional transformation of data, so that now we fit X and Y, and we see just 3 lines, and all is okay. And now let us plot our data. This is the two clouds, blue one and the red one, and you see that the divided hyperplane, in this situation the hyperplane is just a line which divides the plane by two parts, and one part is blue and the second part is red. If you would like to know how to construct such graphs, you can look onto the link in the video description. Now we have studied the very foundations of linear algebra used in data analysis and machine learning. Now you are able to operate with vectors and matrices, to solve systems of linear equations, to find bases in vector spaces, and to provide the orthogonalization of such a basis. Also, you can construct several matrix decompositions which are useful for applications. Moreover, we have discussed the linear regression model for finding dependencies of features and a linear classifier such as SVM to separate classes of data. Note that these are only the first steps toward linear algebra applications in data analysis. There are other useful methods such as principal component analysis and methods of dimensionality reductions. These methods are based on such concepts as the concept of eigenvector and other matrix decompositions such as SVD. These are studied in extended courses, in particular in master programs. Still, in our final project, you'll try to predict a human lifespan across countries using statistical data. Firstly, we recommend to use a linear regression to model the life expectancy prediction. Moreover, this model would allow you to find the most important features which mostly determine the life expectancy. Then you would use SVM to separate the countries into two classes based on these features. I hope you'll enjoy our project, and I hope you'll enjoy using linear algebra in applications.